So I'm really excited to moderate this session. I don't think we need
It's for the online audience.
Oh, I see, okay. Can you hear me? Yeah. So talk about NOAA collaboration with NASA. It's a big topic, I understand. I won't spend too much time. I just want to emphasize there's a session in the afternoon. We have our speaker was not able to come, so we have one session open. So think about some open questions in the meantime. Either you can put it online in the app if you log in, or write a note and send it to me, and then we can put together more time for open discussion. So it's my pleasure to introduce your first speaker, Mitch Goldberg from NOAA NEST's chief scientist.
Thank you.
He have long resumes, and then working in NOAA for a long time, and NEST's different division, meteorology, and collaborating with NASA. He's a fellow AMS, I want to emphasize, and then I've been affiliated since my graduate school time, AMS. He have a PhD from University of Maryland, and I have a most distinguished alumni award from the department. So welcome, Mitch.
Thank you, thank you. I think I'm the first and last speaker, right?
You are the first and last speaker.
Last speaker. So, thank you for inviting me, number one. I think the presentation is probably 40, 45 minutes, so pace yourself. And I am a meteorologist, not an oceanographer, but I'm learning a lot. I had a lot of help on this presentation by Paul DiGiacomo, who's the division chief of the Satellite Oceanography and Climatology Division with the NESASTAR, and Veronica Lance, who's also a NESASTAR, and Ross Parson, who's with NCI. He's the deputy chief of the Oceanographic and Geophysical Science and Services Division in NCI. So I think everyone understands climate change and the impacts that we're seeing, sea level rise, more coastal flooding, more extreme weather events, increase in ocean heat content, salinity, changing fish habitats, more harmful algal blooms, more severity, and more beach closings and things like that. So we're seeing it, right? It's not going away. And so what we're doing within NOAA is that we want to make sure we provide the right information to communities so we can mitigate the impact for climate change. Because even if we reduce greenhouse gas emissions, which is really important, this impact is going to be with us for a while. So it's really important that we focus on that. And what I'm going to do is I'm going to talk about the big picture, what we're doing at NOAA, so you understand what we're doing at NOAA. Then I'm going to drill down into what we're doing at NESDIS with respect to satellites, and then also with NCI. Then I'll talk about next generation satellites with the geostationary satellites that we're planning. And that's the collaboration with NASA will be that part, because they're our major partner in developing our satellites. There's other collaboration with NASA in the sciences, but I won't really touch on that too much and focus on what NOAA is doing. So NOAA has a new strategic plan that focuses on climate. And so in the first part, we're trying to establish NOAA as the primary authoritative source for climate, just like we do for weather. If there's a hurricane, right, where do you go to? You don't go to EPA, you go to NOAA. You go for NOAA to the Hurricane Center. And so we want to be that same source for climate. We want to work in terms of environmental stewardship, economic development, in the sense of providing that information so our economy is resilient to climate change. From current, providing information on current conditions, but also projections way out into the future, so one can plan, do we build more seawalls and things like that? What do we do? How will species, fish habitats change over the next 20, 30 years? That's really important for the blue economy. And of course, equity is really important. Equity, making sure that we're providing services to all communities, especially vulnerable, underrepresented communities. So that's really our NOAA priorities, and we have this 2030 vision statement of climate-ready nation, a thriving nation whose prosperity, health, security, and continued growth benefit from and depend upon a shared understanding and collective action to reduce the impacts of climate change. So that's really our mission, is to provide that information. The vision for the new blue economy basically says what I said earlier, a sustainable and equitable ocean and coastal economy that optimizes advances in science and technology. That's what Nicole talked about earlier, to create value-added, data-driven economic opportunities. We're very consistent, right, with the UN Decade of Ocean Science for Sustainable Development. So this basically is the objectives, and the challenges are listed here, and what we want. So of course the challenges for the decade is to understand and beat marine pollution. That's really important. Protect and restore ecosystems and biodiversity. Sustainably feed the global population, and so on. And this is what we want, right? A clean ocean, a healthy ocean, a resilient ocean, a predicted ocean, a productive ocean, a safe ocean, et cetera. So what we're doing at NOAA is very consistent to the international message, the needs of the international community and industry and the economy. So what NOAA has done is that it formed a climate council of, led by Dr. Rick Spinrad, the NOAA administrator, and all the AAs, from the different line offices, which I'll show you later. And we have this new group called the Earth System Integration Board, that is basically, so the NOAA Climate Council provides a strategy, overall strategy, even though this document says strategies too. That document is really a strategy implementation plan, what needs to get done. And so we identify these 6 challenges: extreme events and cascading hazards, coastal resilience, the changing ocean, water availability, quality and risk, effects of space weather, and monitoring and modeling for climate change. And what I'll do is later I'll show examples of what we're doing in coastal resiliency and the changing ocean. Basically, we're defining what we need to do over the next 5 years. And the strategies, all these challenges have a similar climate value chain in which we have to work with the community. We want to work with the community, right? Ultimately, this is what we're serving the community. So we want to make sure we provide the right service, delivery, and decision support tools that the community needs. And the underpinning of services, right, is the modeling, make sure we have the modeling right, the R&D right, the data stewardship, and the observations. So you can go this way or that way. I mean, ultimately, everything is underpinned by observations, right? So it goes from, even though it goes 1 to 5 here, one can also think the other way, but it's always really important to not just focus in this direction, but to also look at what the end game is, what type of information is really needed, and then you figure out the rest of it. And this is the NOAA org chart. So what we're doing, we're working across NOAA. So when I showed that previous chart of the strategy, it's not one line office. So these are all the different line offices. So we have Fisheries Service, Ocean Service, NESDIS, which I'm from. OAR does the research. This research across all these line offices, but that's specifically a research organization. There's research within NESDIS, Weather Service, and Office of Marine and Aviation Operations. And so I'm going to now talk about NESDIS. So I'm taking my time, 45 minutes. So I'm going from the big picture to what we do at NESDIS, then focus on the satellites, and then NCI, and then next generation. All right. So at NESDIS, our core mission is provide really the information that's needed by the other parts of NOAA to provide the product and services. But we also generate our own product and services because within NESDIS, which is not just a satellite program, This is where NCI is located, the National Center of Environmental Information. So they collect a lot of data from other, from partners throughout the world, as well as within NOAA, to do these assessments, climate assessments and things like that. But within a key part of NESDIS is operating the satellites and providing the products, developing the science that goes into generating the products, and planning next generation of satellites. So I'll show an example of mostly some of the products and the next generation. And we also provide distribution of data. We have a Coast Watch, Ocean Watch node for a lot of the ocean products and coastal products. So I know we have two types of satellites. Is everyone familiar with satellites, mostly? Okay, good. All right. So we have the polar orbiting satellites that provides us with global observations, right? So it goes from, orbit South Pole to North Pole, and it's in a low orbit, so as it's orbiting in the same racetrack, for example, the Earth is spinning underneath it, and that's how you get global observations. And that's normally the feed into forecast systems. And then the geostationary, of course, is at a higher altitude, 22,000 miles, and it's orbiting, it's moving at the same speed as the Earth is rotating, so it's always overhead. So this is normally used for nowcasting, this is normally used for modeling, but now they're sort of merging together. And you'll see that the next generation becomes more capable, because we're going to actually have an ocean imager, ocean color imager on the next generation. So, so that's good news. I know we operate 16 satellites, okay? Our own, plus also DoD, DMSP satellites. But when you look at the international community, it's a lot more, right? And so what we do is we bring in a lot of data from partners. This is a good diagram that shows the different observations that we collect. So we collect our own observations, right? We build our own satellites with NASA. NASA builds the satellites, we operate the satellites. We get observations from partner assets, a lot of data from Europe, for example, from ESA and from EUMETSAT. We're really turning on the spigot for commercial data sources. That's really trending up. And of course, other information, in situ and other data. And that goes into producing data products, information products, and services like, climate assessments is done within NCI. And these are the services that we feed, right? So we get requirements from the services that says, Weather Ready Nation basically says this is what I need to forecast weather. We have resilient coasts, as you see there, and healthy oceans and climate. So we work with these communities within NOAA, and they work with with stakeholders to figure out what's really needed. And we also work directly with stakeholders. And so we bring all that together and deliver these products. And we're developing systems that are what we call source agnostic. So we're developing the science as enterprise science. So if you have an optical sensor from NOAA or from Europe or from NASA, it doesn't matter. We apply the same science, and we try to have the seamless capabilities. So this is similar to the other chart, or basically it breaks it up down into different sensors. So we have observations from NOAA satellites. We then depend on observations from non-NOAA satellites. Might give us higher spatial resolution from the Sentinels. There's SAR data embedded in here. We don't have SAR data here. There's scatterometer data for ocean surface vector winds. We rely on partners for that. Then there's other partners where we try to get higher temporal refresh and so on. So just the message is that we work in the community, we work across the communities to get the observations that we need. And there's growing user needs. So we're planning next generation LEO, low Earth orbit, polar orbiting satellites, as well as GEO. So we've identified, climate change is also causing severe weather. So even though we say we have a weather-ready nation, doesn't mean the job's done. We still have to improve forecasts. So there's going to be a trend towards higher and higher resolution for short-term and long-term weather prediction. So we still need more improved measurements in that for those services. The blue economy really needs more information on harmful algal blooms and other ocean biology type of information. And we're looking at hyperspectral ocean color imagery with improved spatial resolution. This is atmospheric chemistry. And on the right with geo, also we want to, this gives us the ocean complete global view. And the geo is focusing on the ocean the coastal view, looking at an ocean color sensor, which I'll talk about later. All right. I'm not going to read everything, don't worry. But I want to show you that we're doing all this planning within NOAA. So within the previous chart that I showed, the weather, water, climate strategy, which is the implementation sort of part of the high-level strategy. This is coastal resilience. Remember, these are one of the challenge areas. So here we talk about the challenges, impact of severe storms, impacts of rising seas, the warming ocean, the loss of sea ice, changing ecology, et cetera, that these are impacting coastal communities. And so we have to provide the information. And so here listed, it was the example, what I talked about earlier, about these are what we've said in the next 5 years, we're going to, deliver, for example, more predictive, more accurate coastal ocean modeling, a suite of products to forecast sea state, marine weather, freshwater ice extent, salinity, water temperature, and so forth. Improve our observational infrastructure, get more data on, bathymetry data, and so forth, and water level variability prediction. So there's a lot of, it's sort of a blueprint of what we're doing over the next 5 years. There's more modeling capabilities being developed for predicting biogeochemical change to sea level rise, warming oceans, things like that. Training, working with communities, better dissemination of information, and developing coastal ocean normals. Changing ocean, same thing, but now it's more open ocean, looking at ocean acidification, affecting marine resources, things like that. And then here is listed better forecast, comprehensive ocean forecast, improved ocean physics, and so forth, more observations, and integrating marine and ice information and so forth. And there's another page of more statistics, computing indicators, being more predictive, and so on. And this feeds into our climate and fisheries initiative that we're working on. This is, of course, no, this is, so we're providing the data that will support this. But the whole idea is that we really want to advance climate and ocean ecosystem understanding. So we're working on that, providing these support systems in order to make them, climate ready decision making. So here's a nice informed. So this curve here, this diagram, basically shows its time versus sort of resolution, and so this top right here with the clouds is basically traditional weather scales. And so you have the nowcasting of hurricanes, tropical storms, to all the way to what will seasonal forecast and long-term climate projections. And this, now we use that sort of concept model for fisheries. Real-time industry operations. Then what should the annual catch limits be? What should rebuilding and protecting areas? And resilience is sustainable. It has different timescales. So we're trying to produce these services, to answer these questions. When is a fishery no longer viable because of a shift in the habitat? When can new fisheries start? How should biological reference points be adjusted for changing baselines, and so on? And so, and we're linking climate to marine ecosystem responses, which is really important because things are shifting. This shows biomass per tow, and you can see 1973 to 2019, it's very different due to mostly ocean heat content rise. And so this is what the system's going to produce, information on tipping points and thresholds, ecosystem-wide forecast projections, species forecast projections, and habitat and distribution maps, going from days to seasons to years and hopefully perhaps decades. So now that's the big picture. Now I'm just going to jump into the satellite part. All right. So there's a lot of information being used that is needed for these services. And so now I'm going to talk about the satellite end of it. So Paul is the chief of the Satellite Oceanography and Climate Division that I mentioned in the introduction, in the beginning. He has 3 branches, and they work on these different activities. So I just want to call them out. They do outstanding science and developing different products and working with the user community and so on. They have, on the upper right is a list of products, but they reach out to the community with information-based products and analysis through Coast Watch, Ocean Watch, Polar Watch, Coral Reef Watch. I have some examples later I'll show. And so there's a lot of information. This is what you get from satellite oceanography. You get temperature, of course, right? You get, we're using more and more synthetic aperture radar that can penetrate clouds and see a lot of good information on sea ice and as well as floods and wind speed too. We have ocean color, altimetry for sea level rise, ocean vector winds using scatterometry, salinity, imagery, and sea ice using also imagery optical systems. So we've been using a lot of SAR data, and this is, so NOAA doesn't have its own SAR systems. We rely on partners for the Canadians, RadarSat-2, and the RadarSat constellation to the right, and Sentinel is from ESA, and so it provides a lot of good information. Here's an example of different products and applications listed here. Here's wind speed, so we can get information on coastal wind speed. Impacts a lot of, onshore winds, flooding, and things like that. We can look and zoom into areas where there's coastal flooding, shown here. Blue is where there's flooding, and we also get wind speed. This is from a hurricane. And of course, oil spill detection and ice and so on. This is an example of wind speed from Hurricane Ida. So we get that from SAR, and at the same time we get flooding information. And you can see this is where the, what is it called? Those, where you wall off. What is that? I'm just forgetting. What? Levees, thank you. I just did it. Yeah, I just did not, I couldn't, so you can see where the levees are. Sorry about that. Just had a senior moment. So anyway, so the blue area is where the floods are, and you can see it's holding the water back really nicely. So you can see that from the SAR data. And also SAR, you can actually look at coastal, coastal erosion and things like that. There's a lot of good examples. This is looking at oil spills. So great applications. We have an automated oil spills detection capability using SAR data. Arctic ice, this is ice for a given day. So this is coverage that you get a given day. And you can actually look at ice motion. So that's really important for navigation. Let's see that. Oh, let me go back. Oops, going in the wrong direction. And we're also looking at commercial. So the great thing about SAR, it sees a lot and you see through clouds. The bad thing about SAR is that you don't have it that often, but now the commercial sector is providing higher capability, higher temporal refresh. So we're working with ICEYE. They have a nice constellation of 13 satellites, soon they'll have 18. And this sort of shows the higher temporal refresh that you get. You can actually track ships. You can use that to track illegal shipping. and anything else, you know. And so we have a contract with ISI to start using the data for oil spills and other, other environmental responses, illegal fishing and things like that. So that's exciting. SST, we integrate both polar orbiting satellites and geostationary satellites, and we get high temporal resolution SST. We have ocean color from VIIRS and also from other platforms. We use still MODIS, and we use ESA's Sentinel-3 OCLI. And so it really tells us on the biodiversity of the ocean. And that information, of course, is used for harmful algal bloom detection and so on. And we also can generate research products of showing phytoplankton functional types, which is very interesting. As we know, ocean heat content is rising, and this is changing, shifting marine habitats, and we get a good handle on ocean heat content by using information from various sources. So altimetry is one source. Sea level rise, of course, when the sea, when you have clusters where the level is higher, it's usually related to ocean heat content. And then we combine that with sea surface temperature and also Argos floats, in order to come up with good estimate of ocean heat content. But there's a lot of application of altimetry, sea level rise to forecasting hurricane intensity, and so on. And we bring in the other data, right? It's not just satellite data. So here's the Argo program with the profilers and so forth, and the tropical atmosphere ocean array. And so we bring all that data together, and we look at changes in ocean heat content, annually. It's updated periodically, and so forth. Okay, how do we get the data out, right? So we have something, are you guys familiar with Ocean Watch and Coast Watch? Okay, good. So we have NOAA Coast Watch and Ocean Watch, so they allow us to provide data in tailored data that's tailored into regions and formats, and we make sure the data has quality control, monitored, and provide training and so on, and we get feedback from the community. So we use this as a major portal, and it has a lot of players. There's Polar Watch West Coast, West Coast and Great Lakes and East Coast, and there's Caribbean, Gulf of Mexico, Atlantic Ocean Watch, which is a large footprint. They're also aligned with different line offices within NOAA, and a lot of data providers, external providers, data providers, a lot of users. So we get a lot of good feedback from these programs. The information is valuable, right? We have a 400 million agriculture industry, and it's estimated that because of harmful algal blooms, the cost to that seafood sector is about $20 million a year. So Coast Watch provides that information, additional information. There's also, information from in situ observations, obviously, but we're able to see the areas that are under stress or has these harmful algal bloom issues, and then we can also then use that information to direct more in situ observations to take, more detailed measurements. And so we also use information from Coast Watch to be able to respond to emergencies like the Deepwater Horizon oil spill, shown here. And so that's important. Seascape products basically tells us about the biodiversity of marine ecosystems. And that's one of our products that's updated periodically. And so you can actually see how diversity is changing, over decades. And information on sea turtles on long lines. So, so commercial fishing operations are ceased when longliners accidentally hook and capture and kill endangered turtles. We have information where the sea surface temperature is gradient, looking at these gradients, and knowing where the likelihood of sea turtles will be. So that information is used by the fishing industry to be on the lookout for turtles. And then forecasting. So I mentioned earlier that we have to do better in forecasting, and we're moving in that direction. We have these called CHARM, 3-day forecast of these toxins that's using SST and chlorophyll. So that is moving things in the right direction. Because you don't want to respond to events as they're happening. You want to prepare for events and be able to predict these events. So that's really important. We have tools, for example, monitoring sargassum algae monitoring. That impacts tourism quite a bit, right? And so on. Let's see. Bathymetry is very interesting from satellites because we can see optically, right? And we can actually see, predict, estimate what the changes look like. So I think the next slide shows Oregon Inlet, North Carolina. This is a change in bathymetry along the coastline shown here. So this is all satellite-based information. So it's very responsive to a current event. We have the NOAA Coral Reef Watch that is based on looking at persistent increases in sea surface temperature. So if you have abnormally warm sea surface temperatures for a long period of time, that's going to be associated with high-level alerts. We have really nice websites where you can get that information, and other information is also provided, such as marine heat waves, where they are, and where they're forecasted. And on the right is a 4-month outlook of coral bleaching. So that information is provided. And also sea level rise. We have a good website on sea level rise and showing, where they're impacting, island nations, things like that. And we're doing interesting science with respect to trying to bring in multi-sensor data. So here's one looking at chlorophyll from VIIRS, looking at sea surface temperature. So there's cold sea surface temperatures, looking at depressed sea level height anomaly due to, cold waters. And so we can show that areas where there'll be regions of, which will have rich nutrients in terms of, so this can help estimate fishing yields and so on. So now I'm turning to NCI. So NCI brings in a lot of data from all different agencies and provides these comprehensive ocean atmospheric and geophysical data and collects them and does assessments. So they host the largest archives, and they do assessments and things like that. Okay. And the data comes from almost everything, everywhere. So let me just show an example. And what they do, so this is just a schematic that says observations go into analysis for decision making. And they also have a harmful algal bloom observing system. So they have the World Ocean Database and Atlas, which would collect a lot of data, and that could be used for looking at ocean heat content. They have fishery acoustics data set. They have, and here's, this is their data being used to look at the ocean heat content over time. And they have the World Ocean Database that's periodically updated. And I'm just running through this fast. They have this interesting product that they're collecting data from all types of sources on marine microplastic information. So that's something that you might want to look at. Sea winds product, very important for sighting offshore winds, so you can look statistically, where you have persistent high winds, potential use, and so on. I'll skip this one. And also these high-resolution climatology focus on temperature and salinity and things like that. Okay, last part. We're almost done. goes. So I'm going to talk about geostationary because that's the one that's or is more mature in terms of the planning. So we've worked with NASA and NOAA for decades on, NASA usually does the research missions and things that are more mature is operationalized by NOAA, but NASA is still our acquisition agent in making sure they're responsible for meeting NOAA's requirements, and they build the instruments. They have contracts to build the instruments and to launch the satellite, and then we operate the satellite and we generate the products. So this is a series that goes from the very early days to current. And so for decades, we've been focusing just on weather. And now we're expanding to other applications, air pollution, and to also ocean applications. So one thing that the feedback that we've got is that, we can generate nice images or products of ocean color or harmful algal blooms from polar orbiting data, but a lot of times it's cloudy and we can't use the data. And so the idea is that we know that clouds move during the day and you can composite. And so, and at the same time, we need higher spectral resolution. So we combine the need of higher spectral resolution with the need of higher temporal resolution. And we're going to have an ocean color sensor in geo orbit that should be similar to could be similar to the one NASA is developing called Glimmer. So what lessons learned from Glimmer, which will be launched in the later part of this decade, will inform the development of the NOAA operational version in the 2030s. But this is an example of a bad day in the polar world where you have a lot of clouds, and it's just and this is sea surface temperature, and you just don't have that many samples because of clouds. In a week, if you're in an area that's persistently cloudy, in a week, you can get that composite. But here's an example of a day from sea surface, a day from geo, because the clouds are moving during the day, and you can peek through the clouds and be able to do compositing. So that's really a concept. And so this is similar to the chart I showed earlier. So we're going from just weather applications from GOES-R to more applications or more capabilities, ocean color and atmospheric composition, and hyperspectral IR too. So these are just a list of applications from what we call the OCX. They're listed here. And again, the challenges overcome by GeoXO will really be the cloud cover and the frequency, and also the spectral resolution to do better job in phytoplankton types and things like that. So that's the motivation for a higher spectral resolution. And this is just a summary of what the instrument's going to do, 300-meter resolution. It says a temporal resolution of 180 minutes, but it's actually going to be better than that. And it's going to be able to zoom in or be tasking. So if you only have some harmful algal bloom issue, let's say in the Gulf of Mexico or nowhere else, you can just say, I'm going to look over the Gulf of Mexico and not worry about the other areas. So we can task it that way. And these are just examples of how ocean data is used in fisheries and sardine habitats. And so I already showed the CHARM hab forecast. Again, I think this is similar to what I showed before on the benefits. And here's my last slide. And so the take-home message is that we are entering the golden age of ocean remote sensing. We have a lot of information from the international community. They're doing a great job making sure the data is open and available, open science, open data. And we're also working hard to reaching out to the users. Ultimately, it's the user community that really drives what is needed in terms of information. The third is we're really doing a great job in the evolution of modeling and data assimilation is really accelerating, especially with high performance computing. So ocean satellite data are becoming more important to improve. Usually a lot of times the weather models are decoupled from a lot of the surface properties. from the ocean, and now we're starting to add that. And that's going to lead to a better weather forecast, but also better ocean forecast. And we see significant improvements. A lot of the agencies satellite agencies across the planet is really stepping up and improving, trending to better satellite sensors for better ocean observations. And with that, thank you.
Thank you so much, Mitch. I'm always amazed how many satellites you have to work with and partner internationally. Data go to forecasting models, generate the data to the users around the country, around the globe. So I certainly have a lot of questions, but I want to give an opportunity for the audience to ask questions.
Well, I think it's fine.
For the audience.
Oh, yeah, they have to.
Oh, I see.
It's online streaming.
So, given all the satellites NOAA already has, do you think NOAA is still satellite constrained? For example, could you, instead of 16, could you use 26 satellites or 116 satellites?
Oh, absolutely, yeah. I mean, we do have limitations. We have budget constraints, right? And so you can only do so much.
I guess if you were to wave a magic wand, how much capacity do you think NOAA could still use?
Capacity in terms of?
Eyes in the sky.
Oh, yeah. Well, you always have the temporal refresh component and the higher spectral resolution. So, yeah, we can use a lot more capacity, especially for a lot of the ocean observations. And so, yeah, when you compare, when we look at the requirements and compare with what we're actually doing, there's a deficit, there's a gap. And we have to prioritize those gaps, but there are things like, for example, ocean surface vector winds, from scatterometry. We don't have that. So we have observations from Europe in like 9:30 in the morning. And we have observations, there's an OceanSat 3, which is from India, around noon. But then there's really nothing like 2:30, 3:30. So there's a temporal gap. And that's something that, we have a budget constraint, so we can't fulfill all those temporal gaps.
Just to follow up on that, how much do you think surface sensors could help?
I mean, in situ, surface,
yes,
like
bridge that.
Absolutely. I think it's a composite of you want to have sort of autonomous or directed surface observations in areas that are under an extreme condition, right? So if you have harmful algal blooms and you detect it from satellites will say, oh, there's something there, right? And it will sort of give a relative assessment of the magnitude, but then you want to take more detailed information. So it's going to be a combination of, in situ observations. I would say part of the time it could be directed by satellites, knowing where to collect the information.
That's a good question. One of the slides you show the data buy from commercial satellite. That could be one answer to the question, over the capacity and your data buy.
Oh yeah, that's a possibility. That's why we're looking at commercial, to see if that will help us out as well.
Any other questions, comments, remarks?
Yeah, as you were discussing how NOAA takes on the operational aspect of the satellite and the receiving the data, does NOAA have its own sea truthing or ground truthing operation, or is that, we've worked with NASA on that in the past, but does NOAA have its own dedicated team for that?
For CalVal?
Yeah.
Yeah, absolutely. And we use, for Ocean Color, we basically fund and man the MOBI out in Hawaii. Okay. So we do that as well. And NOAA has a lot of ground-based observations too, but we also use NASA, observations, Pandora, things like that. That's been set up. Aeronet, for example, and we contribute a little bit too in that. We have buoys, buoys and everything else. But we do, each of the set of products that are generated. We have science teams as well as, which includes the CalVal team. First thing, of course, is understanding the quality of the data and looking for these artifacts. But yes.
And is that part of NESDIS? NESDIS?
Yeah. Part of STAR.
Yeah, I remember in addition to CalVal, you also have a team. I remember I visited Nestus at one time, and they have a quality control team also on top of the CalVal.
Oh, yeah.
To do
We have an IC. We have a
systematic, yeah.
system that monitors the level 1B, the raw sensor data continuously.
Yeah. Any other questions?
One question from the commercial satellite perspective. Is the current mentality to say, look at the commercial space and see what is available and then say, we'll take this, we'll take that and assimilate together? Or is the mentality, hey, we have this problem, let's work together and build something that can solve this problem?
The mentality so we had an RFI, I guess the input was due end of October, basically to the whole commercial sector, say, tell us what's available. Here are our requirements. Tell us how you can contribute to those requirements. So we did have that call. But then once we have that information, then we have to do an assessment. How will this actually impact our services? Right, so there's there's requirements and there's funding limitations, and then you have to prioritize. So for example, if you suddenly had a constellation of let's say SAR, SAR constellation, because I showed that example. We would look at that assessment. We would look at what the commercial vendors can provide. Then we have to work through our services. So we look at the service responsible for, the National Ice Center, for example. We would tell them this is what, can come from the commercial sector. And they would have to tell us, well, how will that impact the services? So, in terms of efficiency, effectiveness. So if they say, hey, right now I'm just making up numbers, but let's say they're saying we're 60% effective because we can't monitor sea ice on a daily basis because we just don't get enough data, right? And so going from 60%, we can get up to 90%, let's say, with commercial data. And they would have to basically explain to us what that impact is. And then from there, we would determine the cost-benefit analysis, right? It's because, I mean, that's always part of the analysis to understand, what is the benefit from acquiring more data. So that's part of our assessment work. Yeah.
Very good. Any other questions?
I just want to start with sorry.
Go ahead, please.
I was wondering if you could talk a bit about as more satellites come online and the new satellites have even higher data streams, what's the plan or procedure for you making that data available to people besides, the traditional satellite user of National Weather Service or scientists, things like that? What are the thoughts on that? I wonder if you could talk just a bit about that.
All our data is archived, and it's accessible. So you have data from the archive, but it's accessible within 4 hours, 6 hours. So it all depends. If a user says that, well, I need all this information, but I can live with a delay of 6 hours, then all that data is available. The raw data is available. But then we're also putting more and more data into the cloud, and so people can also access it from the cloud. The big data provider is very interested in a lot of this NOAA satellite data. So for example, our geostationary data is available in the cloud now, and I think we're moving JPSS up there too. And so that's one way of providing the data.
Yeah, that's a good question. One of the slides Mitch showed on the ocean data, this Ocean Watch network, they have a regional Ocean Watch centers, and then those center personnel talk to the customers and closer to the users, so they try to understand what they need. Do you need a phone app? Do you need a website? And then how do you get the data in a friendly format deliver the last miles. And then
Yeah.
I think there's a lot of effort, different satellite, and then try to
Yeah.
deliver that data.
I
to
think it's
users.
all levels of service. So for example, if you're doing weather forecasting and you need data immediately, right? Then that has a higher level of service with backup systems to make sure that data is delivered at 99%. Now, if you're a user that says, I want ocean information, but it could be 6 hours old, then that's easier to deliver that, and that's from the archives. So it all depends.
Yeah, I'm not sure how this is going to be relevant. I'm just curious about some stories, right? Like, have you ever said, wow, due to this technology, this particular thing we have right now, we have actually been able to have this kind of an effect in a real world situation?
Sure.
I mean, any kind of stories like there, you go, wow,
I
we're
know.
glad we have this
I'm thinking
technology.
of like, well, I mean, does it have to be ocean stories?
Anything. just go.
So I know there's a good article in, if you look up New York Times, Great Floods of 2019, I think I got the year right, yeah, 2019. There's a great story how the National Guard used our satellite data to know where the Midwest floods were. And they were able to figure out where to rescue people. And FEMA uses our flood products as well, and coastal flooding products as well too. That's always important. Satellite data for ocean applications, ice monitoring is always critical. There was one where we have on VEERS, we have something called the day-night band, and we have imagery at night. And there was, I think it's called, yeah, I know, it's a crabbing ship called the Kiska Sea. And they were stuck in the ice. They just didn't know how to get out of the ice. But they had lights on the ice. And so they called up, I think the Coast Guard, and the Coast Guard called the Weather Service up in Alaska. They were in the Bering Strait, Bering Sea. And they were saying, hey, we're not sure. Of course, you know where you are. They didn't know how to get out of the ice. And so the Weather Service looked at the VEERS image, and they said, they basically gave them, go this way, that way, so forth, because they were able to see where the ice was at night. And they knew where the ship was based on the light. But I guess they would have known where the ship is anyway, right, through GPS. But they were able to go through the maze of ice by looking at the imagery. So that's a good story.
I can add also the story. 20 years ago, there's no measurement of velocity in the coastal ocean. So when someone was lost at sea, got a report, the Coast Guard fly helicopters, they had no idea where the body or the object being drifted, north and south and east and west. Basically, they drop oranges. It's a drifter, we call it oranges. They drop oranges and then say, where the drifter goes? Go to the east and the west, and let track down that way. So that's 20 years ago. In the last decade, NOAA has been funding this coastal radars, and it's basically it's a remote sensing. It's not satellite, but you have this line of sight radars on the coastlines. You send a signal, look in the Doppler return. You can measure the velocity, and that data along the entire California coast now is fully populated, assimilated data every hour into the models, forecasting to the future. The summer report, the Coast Guard put the GUI on the helicopter, all the simulated trajectories, and then north and that the circle I'm going to search, and then is that 10 miles, 20 miles, or ellipses, and then orientation of ellipses, right? So any kilometer of better forecast or translate in the probability of saving lives, and how many ships do you need, how many helicopters you need.
Sure.
So it's a huge kind of the story from the data to the platform all the way to the decision making, and then the pilot helicopter access those data real time.
Yeah, I think any major event, like any worst case, you think about a bad event, like if you have an oil spill, how do you know where the oil spill? You get it from satellite data.
Exactly.
If you have coastal flooding, you get it from satellite data. If you have, I'm thinking of like, even the coral bleaching, you get that from satellite data, and also the profile data. So there's always a mixture of satellite and in situ data. Yeah.
Yeah, this sent
Right.
speaker, sent to Mitch again.
Well, thanks. Thank you again. Thanks for inviting me. That's great. Good discussion. Thank you.
Yeah, we'll continue the Q&A during the break and then in the network later today. Let's move on to the next panel. Panel 2. This is the title: Satellite Monitoring, Tracking, and the Reporting. So we have two presentations scheduled in this session. First presentation, John Marcus from Norbit Subsea. Is John here?
Yeah,
On the way.
yeah, and I just got a call from another gentleman who is also on his debate, so it's just going to be
Is Adil here?
yeah, Jack will come as soon as you arrive.
Is Adil here?
Yeah.
Oh, nice to meet you. Thank you. So maybe we can start with your presentation first, if you don't mind, and then we can we roll Adil, the second presentation of the session scheduled. Briefly, I just do a quick introduction. Adil from Marine Traffic. Welcome. You're based in Los Angeles. Thanks for driving and apologize for the traffic. Living in LA for 20 years, I know the pain. I share your pain. Now I live in San Diego, so. So Adil is the leader in the maritime industry and expert in supply chain, maritime intelligence. He is a co-founder of many startup companies in the maritime space, and he's a graduate from the Y Combinator startup. So many of you know Y Combinators. That's the gold standard for incubators for starting companies. So, so without further ado, Adil, take it away.
Perfect. Well, good morning. Still morning time. Great to be here. Thank you, Matt, and everyone for the invitation. So I'm Adil, and we'll be talking to you about satellite monitoring, reporting, detection, applications. But in the nutshell, it's more about how a data layer, which we utilize as AIS, Automated Identification Systems, can be fused with various other sources of data. So in that fusion, what can you solve based off of an objective? So just to start, figured I'm going to throw out the little Play Store QR codes. If you want to download our app, it's totally free. It's so fun. You can look outside the coastline of San Diego, see what's going on right there. There's an Android QR code, and there's the iOS. So I'll give you guys a minute to zoom in on the appropriate one. I like to be in a more dynamic space, so if you have questions during the presentation, don't feel bad to interrupt me. We're happy to answer them on the fly. But I think just a few more phones. All right. So a little bit about marine traffic. We've been in the commercial sector for over a decade, and our primary value prop is we are a maritime intelligence provider. And like I stated earlier, we utilize data based off of AIS. AIS, in a nutshell, was mandatory based in the 70s as a collision avoidance system for vessels. So vessels would utilize a range bearing on their position to alert them to any potential risk. In case there's inclement weather, you couldn't see them via radar or visually. So AIS helped to produce a way to see what's in the cloud, what's in front of them that is not obvious. And with this data, what we've been able to do is put a lot of analytics behind it, a lot of fun, cool algorithms, and we can see things that have occurred in the past, how they are in real time with the present, and in the next step of every industry is predictability, what is going to happen in the future. So a little bit more background on AIS. It is the Automated Identification System, and the ways that an AIS signal can be obtained are two means. One, little ground terrestrial stations. So we have a global network across many different countries, and they act as antennas. So when a vessel is within a vicinity of the shoreline, and the vessels are pinging their positions and other data, we can collect it via these ground stations. Now, think of it as your favorite radio station. The further away you get from it, you start to build static, and you start to lose that station. So we've partnered with various satellite commercial vendors as well. So we supplement that gap via satellite AIS. So every geographic region in the world has a certain limitation, and that limitation can change dynamically because of weather factors, for example. So today you might be able to catch a vessel 50 miles offshore of San Diego. Tomorrow you might be only able to catch it 20 miles offshore via the terrestrial station. So we can supplement our data with the satellites above. Now with AIS, like I mentioned, its core was a collision avoidance tool. But what you do with that data can be endless. And I had put a poll for this session, so by all means, if you want to respond to them, I'll let everyone know what the responses were from the audience. Many different use cases. And it could go into safety and security at sea, security from a maritime domain awareness for countries, for their EEZs and territorial waters, transparency in many regards, in fishing cases, logistics, supply chain, energy for a lot of offshore survey work, for drilling purposes. There's many different uses of AIS when it comes to those types of operations. And it boils down to finance. Wall Street is a huge user of AIS because they can track commodities worldwide and place their bets and see what hits. So there's many, many different ways that data can be utilized and again fused with other data sources to solve a problem. So when we talk about AIS, what type of data is typically reported? So I took an example from a vessel yesterday, large. Got to put duct tape on that one there. That's funny. So this container ship, for example, just looking at the screen here. So by law, and this is a loose term, captains and officers on watch should state their intent. So they should state where they are departing from and where they're destined to in that leg. This provides authorities some awareness of what this vessel is, where they're going, what their purpose, et cetera, and then they can also implement an ETA. And that ETA can be, it's what's called a reported ETA. So the captain can say, hey, I'm going to take this 10,000 nautical mile journey, and based off of my voyage plan, I anticipate getting there at this time. So very dynamic data that could be inputted by the crew. The AIS is connected to the navigation equipment on the bridge as well. So there are other sensors feeding additional info, such as the status, which from a range traffic perspective, we can derive certain moves. But in certain cases, if it's moving, it's underway, speeds, courses, load conditions, draft data from vessels. A lot of vessel owners, charterers, they require ships to update their draft because that can be important, especially if they're going to be going into certain areas that might not be a deep draft yet, and those vessels can't go in. So other information that's part of it, of course, is positional. And from positions, you can make a lot of cool data, heat maps, etc., and show the past whereabouts of a vessel. In this example from yesterday, this AIS source was via satellite. And generally, we get an update every 3 to 5 minutes via satellite. On the terrestrial spectrum, it's about every 1 to 2 minutes. Weather data, this comes in from a fusion of a weather partner, but also if there is some data being transmitted and fed into the AIS from the vessel, that can be captured as well. So you can have eyes on the ground at the vessel level. And talking more about the ETA, So what we do is we can also put in our intelligence behind it based off of the historical data that we've had. So reported ETA, there's a capped-in time frame. We run our own calculated ETA based off of historical events, vessels of a similar type, of a similar class, on a similar route, and we spit out what we believe will be that ETA, because vessels are not like cars where you could do 60 miles an hour. Vessels cannot maintain a static speed. So that speed impacts arrival times. Based off of those routes, the distances, how long is a voyage? How much has it traveled? What is that time frame going to be like? And just showing a little example down here for the draft. There's a reported draft. So in this instance, the captain has reported a 14.2 meter draft. We know and understand that that vessel has a max draft of 15.5. So from a commodity perspective, a use case could be roughly how many tons of cargo are on board the ship. And of course, there's other ballast requirements, and that drops down the vessel's draft. But some type of value can be constructed based off of this value. So taking all that information, we can view the global maritime market. And we've, like I mentioned, have about 10 plus years of data. And with AIS, it needs to be cleaned up because it's an old tech. It is going through a next generation, a generation 2. So if you actually were to consume AIS data, pretty much the whole globe would be populated with noise. So we have to clean it up to make sense of it. And further to those analytics, we've done a lot of work to geofence ports, anchorages, and terminals. So there are thousands of them across the globe. There are, of course, major ports, and then there are mid-size and small ports, microports as they're called. So when we geofence based off of activity of vessels that have sat there statically for X duration, then we can say, hey, this is Pier 300 Terminal Alpha. And we can then start to derive our activity that otherwise would be delayed information. It happens a lot in logistics and supply chain use cases where a carrier says, hey, the vessel arrived on the 15th. Whereas the vessel actually arrived on the 14th at noon. And that's because that real-time intelligence is, from a carrier perspective, it's not their business. Their business is to move cargo. But from our perspective, having real-time visibility allows, again, many different use cases to come to some conclusion with better data. At the same time, the routes. So this is a heat map that's created based off of a certain vessel type, of a certain class, and we can see those heavily used, as they refer to, sea lanes of communications. So these trade lanes. So forecasting these routes based off of a vessel's intent, where they're departing from, where they're headed towards. You can start to say, hey, are they going to be on that usual path? Or maybe they're deviating. Why are they deviating? What is the reason behind that deviation? Why is the speed potentially slow? If weather is a reason, then that's a pretty simple thing to answer. But there's a lot of different factors that would impact a vessel's transit for a certain route. So these patterns can be stacked week by week, month by month, year over year, and you can start to see how the market changes over a span of time. What's very interesting is in the fishing space, for fisheries. I've seen a deliverable that our data team did for fishing outside, south of the Bering Sea. And over the last few years, there's been this shift of fishing vessels starting further and further west every season. And I didn't dig in too much of it, but that was a very interesting notation that the data team found just based off of a fishing fleet. So on a daily basis, I checked today, there's about 337,000 vessels that are active today. And we collect all their positions. We can derive events based off of those geofences and other factors of the AIS. And we can build the world map. This is what is happening in terms of very well-traveled sea lanes by vessels, their types, etc. And this is the screenshot from this morning, or yesterday actually, just to showcase how the global market is moving. Green, and you'll see it on the app as well, represents cargo vessels, so that could be bulkers, that could be container ships. Red represents tankers, wet bulk, so they could be gas carriers. They can also just be wet bulk for oil. The pink-ish one, those are pleasure boats, so it's kind of fun to see seasonality, how everyone with their nice yachts tend to go to the Mediterranean in the summer times. Blues represent tugs and the offshore market, and peppered around are these little orange ones, and that is the fishing fleet. So you can start to see activities of what they're doing seasonally, but fishing vessels are generally old. They are running on slim margins, and equipment is subpar. So they utilize another class of AIS called Class B, which is a lower powered. It's a little harder to find in very congested waterways. And a lot of times they just shut it off. And you can't stop them from doing it. So then they go dark. They don't want to reveal maybe their secret fishing areas. So there are ways to supplement it and fuse it with other data layers, such as satellite imagery, for example. So I wanted to talk about a use case. And since we're talking about satellite applications for reporting and monitoring. And there was a really fun, I guess, investigative case about fake tankers. So it was this whole Where's Waldo scenario. There is a very large crude carrier called the Diamond II, and it can carry over 2 million barrels of product, which is a lot. But it started to portray a lot of strange behavior. And a lot of times, the vessel in our system would pop in and pop out sporadically, and they would be in different parts of the world. So it never made sense. And there were players that were very interested in finding this vessel. In the whole scheme of things, it was aided by a supply boat called the Iron Man to act like the Diamond II in order to cloak it, to prevent anyone from actually finding this vessel, mostly because they were doing illicit activities. So fusing the AIS intel along with sat imagery helped to reveal the circumstances and the truth of what was taking place with this vessel. So this is a picture of that vessel. And just for an example, this is the last ping this thing had been decommissioned. The intent from this was, I'm leaving this anchorage and heading back to this anchorage. But we can see here that they departed in May and arrived back in October. Weird. Doesn't make sense. So that begged the question as to why. And certain authorities, they require that vessels have their AIS on and transmitting properly. Otherwise, they may not be allowed into their waters. So why does this gap still exist if it's crude carrying? It's going to be passing through different ports where it should be transmitting its intent. And what sprouted this was a lot of sources would start to say, hey, I found this boat. It's sitting over here. And it was completely off of what someone else, another source, said, and maybe a week later. And what's interesting is that the Suez is a shortcut for a lot of oil out in the Middle East, going to the Med, going to Asia, etc. And the Suez has a mandatory rule, you have to have your AIS. But this vessel would bounce. But then there was no record of this vessel transiting the Suez. So we dug in, find out why that was the case. How can this vessel that's so big slip through so many hands? And we started to work backwards, see what else is exhibiting weird behavior? And we came to one short-list vessel called the Iron Man, and it's a supply boat vessel. And the Iron Man was originally owned by a Dutch company and would traverse mostly for oil and gas survey work up in the northeast or in the European area. And then all of a sudden it started to have activity in the Indian Ocean. And that was kind of strange because of what type of offshore work was being done out there. You have to look into sources, see what's actually active. But it just didn't make sense for a while. And we started to dig into its past history, and we started to figure out and plot where these last instances of the Diamond II were, and then put our shortlist vessels and see, are they somewhere close to that vessel? And we started to see a more erratic behavior in the Mediterranean, where the vessel would just stay there. So it wasn't typical of a supply boat behavior. And coincidentally, this vessel got sold to an Indian company under a new flag. And that started to think, okay, well, maybe there is work that needs to be done in the Indian Ocean, in that vicinity, that part of the world. But things still pointed that it was odd. And from one instance, we saw the Diamond II goes back online, but the Iron Man goes offline. Two very separate ones, but weird behavior. So we thought, how is this possible now? Because the last time that we were told of this vessel's whereabouts by some source that visually saw it, it was not anywhere near the Suez. So we asked our friends at Tanker Trackers and Planet Labs, and at that time frame, they were able to have a satellite in orbit and take a picture, see what was there. The point where the Diamond II went online is this vessel right here. It is not the Diamond II because it is too small and the characteristics do not make it a tanker. That is the supply boat. So from that basis, we knew and we started to follow the tracks of the Diamond II, which was the tug. And the tug would act like that tanker to throw people off. And the tanker could go off and continue its illicit activities. So this was a great use case. A lot of governments were really interested in this vessel. And it was just a fascinating chain of events. But this is a very good example of how AIS can be used to supplement additional data layers to find the truth, tell the story, monitor, and see what is going on in the market. Tomorrow there's another panel, and we're going to be discussing ocean data. And in that regard, there are a lot of different use cases there, but it will be focused mostly on vessel bridge data from a more real-time view, so a virtual bridge. And there are things that we are working on to tap into that bridge and also collect additional data that's just stuck in system silos on board vessels. So when we could take that data and from a weather perspective, have actual weather observations live versus crews that are doing the VOS, the Voluntary Observing Ship Program, that they send an update of weather every 6 hours, for example. That in turn can help produce better weather routing, make ships transit safer, smarter, more fuel efficient, more sustainable. And in this instance right here, this is just a snapshot of what happened when the Suez got blocked from the Ever Given. And this showed diversions of vessels from their usual paths to take longer routes. And for them, it made more sense financially to spend the extra money, but this can show how it can impact, one instance can impact the global market.
So what did the Iron Man actually do? Did it clone the AIS platform?
Yes, so there was an instance, so that last, similar to this situation, the Iron Man had rendezvoused with the Diamond 2. And what they did was that they had another AIS transmitter. And so they reproduced the Diamond 2's information, because usually you have some authorized person that comes in and that knows what they're doing with AIS, installs it on the bridge appropriately. So they pretty much installed the second AIS on the Iron Man, mimicking the Diamond 2, and then pretty much just went off on its way. But this is an example of data that's locked in silos from the bridge. The bridge is connected via different means. They could be mechanical means for getting propulsion data, for example, but can't really collect a lot of that. But when you can harness it, you can really unlock a whole different view of the maritime world. Please go ahead if you want to reach out to me. That's a QR code. We'll save a contact card onto your phone. But thank you so much for your time.
Thank you. It's fascinating how many strips you have to track. As you know, over 90% of the cargo coming from the ocean, right?
Yes.
So maybe we can take the time to see if you have any questions. Is John Marcus here?
Janek is here.
Oh, okay. Hey, welcome. So, okay. So we're ask a few questions.
Jonathan, and you're Jonathan.
Who have a question? You want to finish the presentation? Maybe we can cue the question later. Thank you. Okay, welcome, John. Sorry, you're the speaker.
Yeah.
So, sorry for the incidents and
From Norbit.
yeah, for Nordic Subsea, right? So thank you for making the effort to arrive. Just
Yeah, it was a little bit stressful.
That's on time.
Having a flat tire on the roundabout, but
yeah, appreciate that. And then
we made it.
yeah, take it away.
Okay, how do I switch? Just this
There's a
button.
clicker there. Yep.
Okay. All right. So I work for Norbit ASA at our subsidiary Norbit Limited USA. We're a manufacturing company of various products. We have a marine segment. We have a segment of sort of RFID chips and tracking cars and trucks on the road. So we're really a technology company. A few years ago, we decided to make a sonar, and it turns out that everybody wanted to buy it. So that's where we kind of like our focus now. But for today's panel, I wanted to show another product by one of our acquisitions called Aptamar that we acquired maybe 5 years ago. And I think we're about 30, 40 something years old. I think we were founded in 1976. So along the way, we've done a lot of stuff, and now we're doing some acquisitions. So CCOP software by Aptamar is a new release from the Aptamar product line. It is software-centric, and it can ingest a lot of different data sources, as you'll see. This device here was where they started. This is a 6-axis stabilized observation platform that can take FLIR and top-of-the-line FLIR cameras and optical cameras and integrate that into a platform that can be used to observe various things. Mostly where we focus this product line is Norwegian Coast Guard, oil and gas operations, safety of navigation, safety of fisheries. These are all hugely important issues for Norway. How do you maintain an oil and a healthy fisheries industry? So this is a product that came out of that focus in Norway. So the software I'll be talking about today is called CCOP, and COP, it's not Citizen on Patrol, it's actually more like a Common Operating Picture. So it's an integration platform for data that allows the operator to sort of not fuse data, but visually fuse it, sorry. It's been in development for 10 years, and it builds on top of the other products that we've done in the past. It's very software-centric, so primarily we're in the oil and gas field, but we're also getting into vessel management systems, AIS, looking at pollution and stuff like that. So the concept is that we can fuse visually any sensor, no matter where the data is coming from. Today, when we're talking about satellite data integration, most of what we do is integrating satellite data for reference, but you can do a bit more than that. We use Kongsberg Satellite Data Services. Oops, went the wrong way. So we're sort of platform agnostic. So just give us the data, put it in the right format, and we can deliver it on screen is kind of the idea. And you'll see on one of the slides here, it's one of the this shows our market segments. Mostly, we're in the environmental monitoring, especially oil and gas, and which actually goes into security. We're trying to pull the product into more of a security space using our subsea sonars. I'll be presenting tomorrow about what we're doing in security using acoustics underwater. That plays in here, and then vessel tracking. Just over being able to consolidate all of this disparate data and then be able to make analysis and drive information from it. Sales guy's favorite slide. I hate this slide. It's too much info, right? Basically, the point is that satellite data is just one of the layers that we're bringing in to CCOP. And it's treated as a layer like Photoshop or something like that. And you can geo-reference it, and you can overlay millions of other interfaces in. And then the important thing is to recognize in this slide that on the left is the sensor is coming in, and the right is how you view the output from the software. So we support cloud-based, secure, real-time monitoring of oil and gas operations 24 hours a day, 7 days a week. That's a service we provide. We use the software. There's gigabits of information coming in per second, and somebody's actually watching that for the sole purpose of making sure that there's no oil spill or polluter. So we can take in data from sonars, ROV information, USVs, usually they have a sonar on board if you're using them. We can do environmental sensors, subsea, like current profilers and sound velocity and oceanographic metadata. Also, we're looking now at including sniffers for emissions. So we can, and you see here, we can put a sniffer on a drone and then fly it out and actually real-time the data back to somebody watching. And you can go out and interrogate various vessels coming into a harbor. That's kind of the idea. In order to enable the integration of all this data and make some sense of it, we have a workflow package. It's called Workflow, which is a great name. It helps you identify what do you want to get out of this data, what decisions do you need to make, and what can you derive from the data that's coming in? And it's as complicated as the amount of data sources we have, but you can basically create routines to automatically generate alarms based on some of the sensor output. And this is especially useful in the case where we're using third-party detection software to take in radar or satellite data, then process it, and then make it some kind of decision about what's there. So from that output, you can tailor your workflow and your processing and your monitoring according to what you need. So here's a simple example of satellite data overlaid in the real-time software, and then we have AIS data where we also integrate polygons to represent ship size. This is an oil and gas operation off the coast of Norway, FPSO, and supporting vessels. And you can see, for us, satellite data is really the fundamental base layer that gives the context of what the user is looking at. And it's actually really important. This data can be updated every day, so it's not like we're taking Google Earth images from 5 years ago. Some of our customers pay for satellite imagery updated at a very fast pace, which is expensive, but if you're doing oil and gas operations, it could be important. Let's go back. So this is how we bring in geo-reference satellite image data, and then everything else that you see here are... I always hate when I break the door handle. All these other objects are just layers that you can build up on top of your satellite image to provide more awareness. So, and then over here, this is not perfectly related, but here's a radar image integrated as part of a data stream, and also here we have real-time video from one of the vessels. All of these vessels have video. You can just select which one you want to see the video from and tailor this whole thing to what you need as an operator. This slide shows a bit of more like moving up towards the intelligence layer. So what they've done is they've used radar to detect an oil spill. You've got satellite image overlaid in the background. An operator has gone and made a polygon that represents an oil spill. Here what you see is that polygon projected onto radar and video image. So this is the 3D aspect, is you can see your ship overlaid on, if you're doing any operation, having this level of data fusion provides not necessarily a perfect enhancement, but depending on what you're looking for, it could be critical. And so let's move on from there. All right, so I came up with like the simplest example I could to demonstrate how we take satellite images and AIS data, let's say, and use it in a context that is protecting fisheries and related to oil and gas. Oil and gas operations in Norway are incredibly regulated. Fisheries in Norway are super important. Oil and gas is also how they fund their entire country. So balancing the two is important. So 24/7 monitoring of all operations in the North Sea done by Norwegians it's just like what do you call it? They grow up with that. There's no other choice. It's heavily regulated. So I thought this example would be interesting because it's not like a typical oil spill, but it shows how we use the software to detect something more subtle. So incident discovery. So let's talk about what's an incident. Well, that's where somebody spills oil in a protected area. How do we detect an incident? Well, you could send an entire fleet out with sniffers and try and do it that way. Very expensive to patrol. Or you can use satellite data. So what we see here is an oil slick left behind a vessel. It has the telltale signs. An operator can see this in a day-to-day review of satellite images and pick it out pretty clearly. You can also confirm it. If you go on site, you could confirm it, but that's very expensive to go and deploy a vessel with sensors just on a hunch. If we overlay AIS data, then that's it, just another layer. You can see the exact vessel ID that is most likely to have caused that oil spill. I mean, it's just a beautifully simple example. 2 data sources, 1 operator. And typically the AIS data is coming from VHF or UHF radios. And I inquired about this because I'm not like, this is not really my product, but they gave me enough info and training. We also have, we offer satellite enhanced AIS data. So if you lose your radio contact, you can still get AIS data from a satellite. So I thought that was a good example, of how we just fuse 2 data sets really simply to solve a major problem. And that's not unique to the software. I think what's unique to the software is really if we go back and look at everybody's favorite slide is that it's just a big giant data fusing product. And it's super simple to integrate anything you want. Now this is commercial. We do work with the Norwegian Coast Guard, but it's not a CSIR or C4 system. It does have the ability to do point-to-point compression for the data, but this is really a commercial system that's used in oil and gas and environmental awareness. So a bit more, we acquired Aptamar, let's say 8 years ago. This is like the team that is heavily involved. So if you're interested in more about this particular software, it is a Norwegian product. It is dual use. I can put you in touch with any of these people, or you can contact me directly after the show, and we can do that. I also sell the product in the US, although my focus in the US is actually security systems using underwater acoustics, so I'll be giving a presentation on that tomorrow. But this is our surface product, and so I hope that made sense. And a little bit flustered after having that incident today, but go ahead.
Yeah, thank you. Thank you for that presentation.
Thank you.
Adil, can come up here? So we can take the opportunity to ask questions for both speakers. So we have a... What's that? Oh, I'm sorry.
I can try and go really quick.
Yeah.
No, go for it.
Yeah, I apologize. So.
I also had a quick question about what you just presented.
Oh yeah, go ahead. While it's hot.
Yeah, you mentioned sniffers on UAVs. I was wondering, how does the integration of that data layer look on one of those consoles, for example? Like you have the satellite,
That's a-
and then there was some
That's a
overlay.
good question. So in raw data like that would be like numerically based, and then
Sure.
you could apply some processing to it, but it wouldn't be as spatial. You could apply tracks
Sure, yeah,
showing, you know, the values at various locations.
cool.
Yeah.
Thanks.
Yeah. Good question.
Yeah.
All right. Yeah, I apologize. Apparently, I have the older agenda. Man, they didn't update. Yeah, please.
Okay, cool, thank you. These are not my slides. This is not the company I work for. Were they maybe earlier in the deck?
It should have been put on. Do we have another one?
No, that's the third
Okay, give me a
Oh.
second.
I also have my laptop, if that would help.
You have a flash drive we could transfer it real quick.
I don't have a drive, but I can transfer it off the laptop.
Yeah, we have a drive.
Okay.
Okay, where we do the transition, any questions? Take opportunity to ask questions now. Both speakers previously, Adil and John.
So what was the illicit activity that the Diamond 2 did? I mean, was it eventually resolved?
Just still curious. Adil?
Sorry, just repeat that question.
What was the illicit?
Oh, good question.
We cannot forget.
It was a Iranian flag tanker, actually. So they were moving crude because they're not allowed to export, sell certain countries. So the owners just they wanted to go dark, cloak themselves, sell as much as they can. There are a lot of ship-to-ship transfers that took place for that vessel onto smaller feeder tankers. But ultimately, yeah, that even till I think till this day, it is an offline vessel. But for all we know, it could still be sailing out there. Just that desire to track it now is not as hot as it used to be because there's hundreds of other examples.
So that was due to time and embargo was in place, right?
Yes. Yeah. Yeah. This case happened in 2019.
Okay, any?
Go ahead.
Yeah. Also for you, you mentioned the voluntary observing ship program. Is there like a consolidated website of ships that participate in that, or is that a very loose, or are they just kind of one-offs that happen to, you group them that sort of just verbally?
Yeah, great question. I used to sail deep sea, and my understanding of the program is that NOAA approaches vessels and provides a barometer, other equipment, and they say, hey, would you volunteer to provide weather data? So vessels can opt in if they want to, it's not mandatory.
Right.
But they are requested to report every, I think, 4 or 6 hours. There's a certain process in place for that.
Yeah. Okay. Thanks.
Okay, sorry for the glitch. Third speaker in the session.
Yeah. Hey, everyone. I'm John Carey. I'm an engineering manager at Cordis Engineering. Thanks for having us. Also, apologies for the scramble at the end here, but I'll try and go through this fast so that there's still time for questions. For those of you that don't know us, we're an engineering services company, started in 1997. The first 10 years or so of our existence was heavily involved in the analysis phase of product life development, but call it the past 15 years, we've come to be a full systems engineering group. So we specialize in the design, analysis, prototyping, and testing of precision systems. Usually that takes the form of optomechanical systems. Optical instrumentation is sort of our forte. And then because we have so much heritage analyzing space, it kind of was a natural fit to start putting optics in space. So that's kind of what we're here to talk to you guys about today. The key bullet here is that Cordis has been working to lower the barrier to entry for people to put their optical instrumentation in space if they don't necessarily have space legacy. Because new space is now cheap, I use heavy quotes there, but not everyone has the in-house expertise to field a space telescope, let's say. So this is kind of a Venn diagram of the two halves of Quartus and where we meet and what we deliver now. So this is sort of the legacy Quartus of the simulation and analysis-based engineering, still about half of the company. As you can see, we had a lot of heritage in launch vehicles and hypersonics. The systems development group, sort of separately and organically, started working in mechatronics, robotics, metrology, and what we found was a really good overlap of both of those skill sets was the field of optics. And so we do a lot of imaging, remote sensing, spectroscopy, laser communication, and yeah, all airborne or spaceborne. So what we'd like to talk about today is specifically imaging and remote sensing and spectroscopy as it relates to observing the Earth, and specifically like the oceans. So this, like the previous presenter, is a very salesy slide that I will try and go over quickly, but basically Quartus's business model is to meet you exactly where you need us. So it could be that you have a pie-in-the-sky idea and need help with requirements derivation, or it could be that you only need some small slice of high-end analysis. But really, like, the sweet spot we like working with is the whole thing, that we like working with scientists, people in academia, startups, where they might have the physics mostly nailed down, but they don't necessarily have an engineering team, and so we can deliver prototypes for them. And I guess these picture examples, we had a customer come to us that basically they were a geology company and had no experience in LiDAR, but they had the pie-in-the-sky idea for a given spatial resolution for both bathymetric and topographic application at the same time. And so we worked with them from requirements all the way up through delivery, and that's kind of the pictures at the bottom here. Another salesy slide, but this is just sort of showing the space heritage has been with Quartus since the beginning. As I said, the first half or so was largely analysis, kind of the keystone analysis project of the analysis group was that they worked on James Webb for 16 years, including all of the modal correlations and testing, and the on-orbit jitter analysis. So awesome that it's taking pictures now. And then the second half of this slide is kind of showing how that has morphed or evolved into also building both EDU units, and we have built a protoflight unit that has been tested and fielded in space. And we're currently working a bunch of projects that will result in hardware delivery as well. So we're really growing into the optical payload in space industry. So on the note of what we're up to now, I decided to just sort of lump this broadly into the categories of spectroscopy, or generally hyperspectral imaging, and remote sensing, because, yeah, it seemed like a good division. So we have a couple contracts right now with new space startups that are developing all the way from the conceptual design level. They want to test their hardware and field their hardware. So one of our big ones is we've gotten to call it the PDR phase of a hyperspectral imager with very tight spatial resolution requirements and a very wide spectral range requirement that a number of, call it heritage large industry people, no bid because they said that the spatial resolution was not feasible, and Quartus said, nope, we will help you anyways. So the application there is they're intended to help commercial operators with the energy, mining, and agriculture industry. Specifically, this one is one of the spikes it's looking for is methane, looking for methane leaks. Another large project we're doing, it's going to be a constellation of at least 8 satellites, is an MWIR imaging system with very tight temporal resolution requirements. And that's because not only is it gathering data for atmospheric ocean land predictions, but it's also working on like real-time detection, or like pseudo real-time detection of specific events that I'm not allowed to talk about, but that's why we're speaking in the generic sense here. One of our big, longest lasting customers is NASA, and they have used us to advance TRL on a number of programs, and they've also helped us develop our own capabilities. So Demeter is a radiometer that we're currently working on. We've built a demonstration unit in our lab that we're currently testing. And then the case study that I'm going to talk about today very quickly is the Strategic Aerosol and Gas Experiment, which is SAGE. And this is the 4th generation of it because this program's been around for like 20 years. But the idea is that you have an on-orbit spectrometer that is looking through the stratosphere at the sun, and it's using occultation to figure out what are the aerosol contents. So what's really cool is that NASA funded an SBIR with us so that we could validate our STOP analysis, which is structural thermal optic performance analysis. And they basically helped us validate the general design approach of using, call it like a optical template or like a general optical platform that other people could customize. So what we're trying to do is, in the same way that CubeSats have sort of standardized the form factor of small satellites, we are trying to make a library of widgets, optical widgets, that people can come to us and say, oh, we want a spectrometer, or we want a telescope, or we want a hyperspectral imager. And we can, with our analysis capabilities, tweak things slightly, and then very quickly get to a proto-flight level in our workflow. And then remote sensing, I'm not going to touch on a lot today, but these are some of my projects actually. One is the Bathy Topo that I mentioned earlier. That is a refractive scanning system. The other is we developed a topo-only LiDAR system that uses a diffractive scan element. And what's maybe unique about that is the hologram used for scanning there was large enough and the waveform requirements were tight enough that we ended up manufacturing them in-house because everyone else no-bid them. So that sort of showcases an example of if our customers require something that currently doesn't exist in industry, we generally like that sort of challenge, and we will do everything we can to figure it out. So I think I already covered most of what SAGE is. This picture kind of says it the best, that you're staring through the atmosphere at the sun and looking for gaps. This is sort of showing the original older SAGE generation products were like full-blown spectrometers, and the current SAGE is basically using filter wheels looking at very specific bands. And so we can reduce this whole thing down to a very small TMA, like a 3-mirror anastigmat, and then our spectrometer detector on the back. And then this is maybe the key slide here, is the SBIR that I mentioned allowed us to take what we had designed for a very specific program and then sort of generalize the approach for a number of other programs. And we now have data we can talk about publicly, as opposed to a lot of our customers, we can't do that. So you can see here, this was the CAD model, went through design review. This was effectively the radiometry model. It was stray light. Then we did our FEM, and then built up the EDU unit, tested it, and you can see the test data and the predicted analysis data on the top and bottom there. We were down to single nanometers off because we were measuring wavefront over temperature cycles, and the focus error predicted was within like 5 nanometers. So we felt pretty good about that. We are now leveraging this architecture in other programs, which is something we hope to do with a lot of future customers. Yeah, I guess that was as quickly as I could go through all that.
One burning question for the speaker. You know, there will be a lie anyway. So.
Yeah.
On your bathymetry work, what depth can you measure underwater?
I can't actually say that. I'm sorry.
Oh, okay, okay. Just want to know if you're competing.
It's possible.
Okay, so maybe we can continue that Q&A during the break, and
Sure.
and then we it's lunchtime. Well, we will reconvene at 1 o'clock for the panel 3. We have 3 more panels, and also there's the opening and the panel 5. So if you thinking about burning questions, you want to have open discussion, we can have a small group discussion together for that session. So thank you for the 3 speakers and then morning speakers as well. Enjoy your lunch. started. It's shortly after 1 o'clock. Welcome back in this cozy, warm room. Really nice. Excited to have panel 3, satellite technology. Could you use a microphone? Sorry. I saw the small room. I don't know.
Online audience.
It's on?
Yes, sir.
Hello? Yeah, thank you very much. So panel 3, talk about satellite technology for combating IUU. I will have 3 speakers this session. I'm going to introduce Julie Angus as the first speaker. Julie, CEO of Open Ocean Robotic. I have to say a few words about Julie because I met her at the CDL years ago. As a scientist, I met many authors, many explorers, but Julie is the first person I know. Is an author, is a scientist, explorer. And Julie had the honorary doctor from McMaster University, so Dr. Angus. So he's also a member of, a fellow of Royal Canadian Geographic Society. So Julie will talk about her journey of the robotic.
Great. Thank you very much, Yi. And I will, I guess, take that microphone and, oh, sorry, you just, okay. Perfect. Okay, thank you everybody for being here today. And as Yi said, I'm the CEO and co-founder of Open Ocean Robotics. And now I know this is a panel on illegal, unregulated, and unreported fishing enforcement from space. And we're not actually in space. We're a USV, so we're on the surface of the water. But we've done some collaborative work with spatial data, and specifically working with MDA, and Peter will be speaking next about how we can fuse the data that we collect on the water with space data to provide better accuracy and detection, and to be able to detect and identify vessels that aren't providing an AIS signature. So I co-founded this company 4 years ago, and we've grown to offer services primarily in environmental monitoring and in defense and security, providing a platform that can be deployed for longer periods of time. It's a solar-powered platform. And today I want to talk a little bit about the work we've done in illegal fishing enforcement, and also the fusing of data like ours with satellite data, because I think there is the potential for this to be very impactful in providing a more comprehensive picture of the marine environment. So, of course, we know that there are significant challenges protecting marine protected areas and monitoring them, especially as, globally we look towards protecting 30% of our oceans by 2030. With existing technology, we just don't have any way to monitor those at the level of detail that we need. So obviously data from space provides a very important and necessary role in that. And this technology is really looking at how we can enhance that with data on the ocean. And one of the challenges currently with collecting data on the ocean is that we're largely dependent on ships, which are expensive to operate in limited supply, and don't necessarily have the ability to monitor the oceans in the way that we need them to. So autonomous vessels, uncrewed surface vehicles, other marine robotics really have the potential to provide a lot of that data that we're not able to get with traditional ways of collecting data. Of course, the advantages of that is often it's a fraction of the cost. These are small platforms. There's nobody on the vessel, so they can be operated remotely, and it has a very small environmental footprint compared to a large ship. Many of these platforms are renewably powered. Ours are solar powered, but even if they're not, you're using a fraction of the fuel that you would with a large ship. So in terms of the areas that we've been focusing on with our USV, we've been focused on largely security, so being able to provide maritime domain awareness using sensors like cameras and AIS receiver. starting to do work in the offshore, so marine mammal monitoring, largely using acoustics to listen for whales. And a large variety of oceanographic sensors, so we can measure a range of conditions and have these run on our USVs as well as weather forecasting or meteorological data collection. So a lot of these are data sets that would work well to complement satellite data and could be used to provide additional information. So a little brief look at our USV. It's relatively small. It's about 12 feet in length. It weighs 250 to 400 pounds, depending on the configuration. It's designed to be renewably powered, so it's powered off its solar panels, so potentially it can be out on the ocean for weeks or months at a time, depending on the power payload. Some of the things that allow it to, excel in some of the applications that we've put it in is that it's very heavily ruggedized. It's a self-righting design. It uses a buoyancy-based self-righting system, so it's a combination of the roll bar and the shape of the vessel. So this allows it to be still relatively light and have a shallow draft. So it's able to go in very shallow waters, but it's also able to go offshore in heavy conditions. It has a modular battery bank, so we're able to outfit it for the type of mission that we deploy. So we've done some short missions where we're running a heavier powered sensor, like a multi-beam, and then we're pretty much dependent on the batteries exclusively. Or it can go for longer offshore missions where it's able to collect enough power to be able to run its systems, motor, and then the battery bank just really acts as a reserve during the night or during cloudy conditions, low solar conditions. It's not a fast boat. It's not going to, do any interdictions. It averages about 1 to 2 knots, but it has burst speeds of up to 7 knots. So that does allow it to maneuver in some areas where there's higher currents or to get to position, in some cases, a bit faster. In terms of some of the testing and then the deployments that we've done, so we have tested it in fairly challenging conditions. This is just testing some of the self-righting capabilities and how it tracks in the heavier sea states. So this is off the west coast of Vancouver Island. We've just put it in the surf break there. So it definitely surfs better than I do. But you can see that it is, it's a really robust vehicle and it's able to go in a lot of different conditions. This is sort of the areas, the verticals that we've been operating in. So we have the baseline core sensor suite, which includes cameras, an AIS transponder, receiver, basic meteorological weather collection data, and then we have some oceanographic sensors like water temperature, depth. And then we have deployed for illegal fishing enforcement, also for maritime domain awareness, and we've added some additional sensors on for that, a thermal camera. We've also used a towed passive acoustic array and onboard processing. And same thing for environmental monitoring. We have several bays where you can put in different types of sensors, so it's fairly easy to utilize and swap out sensors. So we can have a range of oceanographic sensors from turbidity to oxygen, salinity, temperature, those sorts of things. We also have a large sensor mount for things like an ADCP, a multi-beam. So it's a fairly versatile platform, and then we've used it for a number of different applications. In terms of how we deploy, so we don't sell the vehicles, we operate them, so it's very much a contractor-owned, contractor-operated model. So that means everything from planning the mission, getting the permissions, shipping the boat, deploying it, and then operating it when it's on the water, and then providing that data both in real time and afterwards. We operate the vehicle often from our control room, which is in Victoria, Victoria, BC. We have a range of communications, including satellite, so we have that beyond the horizon communication, but we also have cellular and radio, which is valuable in some instances. So in terms of the work that we've done in illegal fishing enforcement and ocean monitoring, I think that's probably most relevant to focus on here. So I thought I would go into some of the projects a little bit. Right now we have a project with the U.S. Navy for maritime domain awareness. We've worked with the Canadian Navy through Defense Research Development Canada. We've done work monitoring marine sanctuaries in Canada as well as elsewhere. In Canada, we have some endangered whale populations, the southern resident killer whale, so we've done work monitoring for those animals as well as monitoring for vessels to see about compliance. And then in terms of illegal fishing, what I want to talk about today is a project that we've been involved in over multiple years. It's called MPA Bots, and it's a multi-year project involving several companies that's really targeted towards helping to have affordable solutions to monitor marine protected areas to deter illegal fishing. And it's a number of different marine robotics solutions. And this program has allowed us to demonstrate, harden, and continue to advance our technology with the goal of deploying it for use in the Bahamas and other MPAs where they have some very specific challenges. And the project that I'm going to talk about is a 25-day deployment that we did under this, and that was done in a Hawaiian marine sanctuary. And we worked with space company MDA, and Peter will speak about MDA next. And we did some preliminary work looking at how we could potentially fuse space data and our data to be able to create a more comprehensive picture, and in particular, how we could use vessels like ours to identify vessels that aren't running AIS or to validate that, and then potentially in the future have a closer integration of those technologies. But really one of the key goals for us in this deployment was showing that we could go out for 25 days, we could collect relevant data, we could operate in a range of sometimes challenging weather conditions that we were to experience out there. So we did that deployment just over a year ago. And we ran a suite of sensors for vessel detection as well as for MPA monitoring, so oceanographic and environmental conditions. And the goal was really to show what that data set might look like and how that data set could counter IUU fishing by providing insights for interdiction, closer monitoring, or even potentially information that could be used for prosecution. In terms of the sensor suite that we ran on the USV, we had a passive acoustic system that was a single-towed hydrophone that collected some acoustic data. We had cameras for visual detection. We had a 365-degree optical cameras and a forward-facing thermal camera. And then we had a number of oceanographic and environmental sensors, including an AirMar weather station, a transducer, an AIS transponder. We had an AML sensor suite for conductivity and temperature, turbidity, and chlorophyll A. And this mission in total, it ran for 600 hours, so 25 days. We traveled just over 500 miles over that time. Some of it was spent doing a grid pattern, some of it was loitering. So it was a range of different CONOPS to test out different kinds of conditions. And we traveled from very shallow waters. We deployed at a boat launch ramp to fairly deep waters. The maximum wind speed we had was 50 miles per hour. And fairly steep wave height. And then the USV traveled on average 1.1 miles per hour, and the maximum was 6.9. This is, how we launched it. We're just at a boat launch ramp in Hawaii. We shipped it out there and put it in the water. It's very easy to launch and control. From there, we operated it, and then at the end of the 25-day mission, it just came back to that same point, and we pulled it out the same way. This is one of our pilots operating it from Victoria. So the amount of data they see depends on if it's on satellite or cellular or radio communication. So when it's on satellite, they're able to see images from the cameras. When it's on satellite, it's much more limited. We have developed a proprietary control program and portal where we can set routes for the USV, taking into consideration environmental conditions, and we can also see that incoming data, and that can be shared with other stakeholders, and of course used for our pilots for navigating as well. This is just some of the pictures that came in. So the images that came in, both optical and thermal. It's a heat map from the AIS detections, so we were able to, monitor for AIS, and this is obviously something else that could be supplemental to satellite data. Collecting this on the ocean and potentially, collecting signals that wouldn't be collected otherwise. And then we did environmental monitoring because we were in these marine protected areas or sanctuaries. We had an underwater camera, so that allowed us to observe some of the environment, and then all the oceanographic and environmental sensors as well. And then, really what's of interest here is how we fuse that satellite and the data that we collected. And this was still a really preliminary project, so we were looking at how we could fuse it in the future, how satellite data could be used to queue a vessel like ours. So, potentially if you have a number of USVs like this monitoring an area for illegal fishing, and you also have satellite data, you see a dark vessel or something of interest, you could have the fleet move towards that and to collect additional visual, acoustic, or other data that would then be of interest. Potentially it could provide important information for AIS spoofing, and then it could work the other way around too. So if you detect something that is of interest, you can get additional satellite information to provide more information for this. So in this case, this is MDA's Maritime Insights platform, and data like ours could potentially just feed into that as another data source. So whether it's images, whether it's AIS detection, whether it's ocean or environmental data that's collected. I think it's exciting. I think USVs do have a big opportunity to add important information for helping to deter illegal fishing, working alongside other technologies. I think just the scalability and, utility of platforms like this that could potentially operate in areas where you don't have other assets for extended periods of time is exciting. So I think, that's it for me. I think it'll be really interesting to hear Peter's presentation next and think more about how these data sets can work together. Thank you.
It's my pleasure to introduce next speaker, Peter Anderson, research scientist for MDA. Peter got PhD from University of British Columbia. Peter impressed me with a number of tools he had been using. CFDs, FEM, GIS, the list goes on. So Peter, the floor is yours.
Thank you. I'm really appreciative for the chance to be here. As Julie introduced nicely, I'm with the company MDA, and let's see if this button goes forward. There we go. So just to introduce MDA at a high level, we have about a 50-year history of space innovation. We have somewhere around 2,400 employees. Most of them are in Canada, but we do have a few branches internationally also. And so this includes space for design, manufacturing, testing, satellite equipment. We break our company down into three main business areas, which are robotics and space operations, satellite systems, and geointelligence. So MDA plays in nearly every sector of the space economy. So we are not doing launch, but after that we've been involved in robotics or on-orbit servicing, rovers, developing satellites and satellite components, and also geointelligence. So, you know, when we gather the data, how do we get it down to the ground, and how do we make sense of what we've gathered? So that's just a really broad view of what MDA does. For the sake of this panel on IUU fishing, I'm going to zoom into just two aspects in particular. And the first of that is our Canadian SAR background. The RADARSAT-1 mission was initially launched in 1995, RADARSAT-2 in 2007, and that is still going. So this is actually a bit outdated because we were excited that RADARSAT-2 has now broken the 1 million image acquisition mark recently, which is a nice landmark. And then RADARSAT Constellation mission, which is a 3-satellite mission that was launched in 2019. And so MDA has played a role in all three of these missions. Just for those, I don't know if everybody's familiar with SAR. Mitch this morning introduced it nicely, but with a different application. So kind of what can SAR do particularly for IUU fishing? You know, it's an active sensing technology, so you send out a radar pulse, you listen for the bounce back, and with that information you can form a picture of what's happening on the ground. So this means we can image through the clouds, we can image at night, and you can also utilize multiple imaging modes. So you can operate SAR in a use case where you're capturing a really wide angle view at lower resolution, or you can zoom in, do a narrow swath, but at high resolution. So you have a certain level of versatility there. Because you are sending out your pulse, you can utilize the Doppler shift effect to estimate ship velocity, and also in some cases a smaller low detectability ship. You might not be able to see the ship itself, but you can detect it by its wake. So those are just a few nice features of SAR when it comes to ship detection. And so something exciting that MDA is working on now is we are developing a new SAR mission. It's going to be a constellation of SAR satellites called CHORUS. And in particular, the CHORUS mission is going to have a nice tip and cue feature that can be helpful when it comes to illegal fishing. So the lead satellite there on the right is a wide angle imager, and so it will take an initial pass, and you might get back a blurry image like that, and so you can say, okay, there's something there, but you can't tell a whole lot about it. But if the first satellite downlinks to the base station, and then we have a trailing high resolution SAR satellite that follows an hour later, which is able to capture a much higher resolution image where you can see, oh, these are actually two ships rendezvousing, and you can tell a lot more about them. And so this tip and cue capability might be useful in terms of achieving like a faster turnaround and following up on what's actually happening on the ground. So shifting gears a little bit, the other thing I want to zoom in on that MDA does is we have our Maritime Insights platform. And so this is more on the analytics side. And we have a cartoon version to talk about what this is. So if you're an intelligence analyst and you're concerned about illegal ship activity, there's all kinds of data that you can pull on: VMS, AIS, optical or SAR imagery, radio frequency detections. These are all kinds of sources. They are quite complicated on their own. So in the Maritime Insights platform, first of all, we fuse them together and then also perform analytics to help highlight, okay, you know, these are the ships that are behaving and these are the ships that are, you know, evidently trying to hide something. And so that can quickly narrow in to say, okay, you know, these are the problem ships that we want to take a closer look at. And so at the end of the day, it really helps the intelligent analyst to, you know, zoom in and say, these are the ships, these are the regions to check out. To provide a few more details on that, we are fusing more than 25 different data sources, and so this is kind of where Julie's presentation fits in. You know, we can start fusing not just satellite sources. You know, here we have 150 satellite sources, but you can think about fusing additional ground sensors and stuff like that too. So fusing a whole bunch of different sources together, and we also support taskable satellites. So a taskable satellite, that means, you know, you have a region or ship that you're concerned about, you can queue up, say, a high resolution optical satellite like a worldview and task it, take a look over here. Because it's integrated, you capture the imagery and you can quickly figure out, get a much better idea of what you're looking at and what they're up to. And then we can start to form tracks. So here at the equator, you can have more than 20 sensing opportunities per day. So, you know, it's getting to the point where it's not just a single view, but you can start to resolve behavior. What's the ship up to? And you can track it and determine, you know, how are you going to engage or react to what they're doing. So the Maritime Insights platform has had, we have 3 operational campaigns. These are happening through the DVD program, which is Government of Canada program, but you'll see the regions that we're looking at are not, they're outside of Canada, so the Government of Canada in support of other nations. So we have Pacific Islands here, Ecuador Navy and Coast Guard, and then North Pacific. You can see these are quite large regions that we are monitoring for IUU fishing, drug traffic, and other illegal activity that's happening there. And so our Maritime Insights platform is pretty exciting. It's making an impact. You know, it really helps the intelligence analysts to zoom in to say, okay, these are the dark targets. These are the ships that are doing something that they're not supposed to. Unfortunately, I can't provide specific details, but in one of these campaigns in the first 8 months, I was really surprised to hear how much, you know, in terms of drugs seized, weapons seized, illegal vessels and illegal people, or vessels and people involved in illegal activities that have been apprehended, protected species and gallons of fuel that have been apprehended as a result of, or in part using this platform. So it's pretty exciting to see what this level of knowledge is able to do and how it can serve the community. And so that's it. That's just an overview of what we're doing. And I'll look forward to discussion later.
Thank you, Peter. We'll hold the question toward the end. So the speaker of the day, of this session, Thomas Gray from Argo Services, part of the Woods Hole Group. I'm a happy user of the Woods Hole Group's and Iridium services for my float. So every time I come to the surface, I know where to dial. So, so Thomas is passionate about open source, so cannot wait to hear.
Sure. So I'm Thomas Gray, and I work for the Woods Hole Group, which is a subsidiary of CLS, and CLS provides satellite services around the world. What we focus on in the Woods Hole Group for North America is primarily VMS systems for fishing applications. My background, though, is not fishing related. I'm actually on the satellite telemetry services side, which is primarily wildlife applications. So we track about 8,000 animals at any given time, as well as some oceanographic equipment. Like if you were here yesterday, I believe it was, there was a lovely talk about the Argo program. We used to be the sole provider of the data through the Argo program. We still provide data through it, but it's transitioned off of Argos and towards Iridium. But anyways, we're here for IUU fishing, so I'm going to put on my fishing hat, and we'll talk about some of the technologies that we use at the Woods Hole Group and at CLS to combat and monitor fishing activities. So we all know what that means. We can skip that. And these are some of the ways that we look at, monitor, and control IUU fishing activities. Sometimes it requires physical hand-to-hand contact when they are landing at port. But this talk is only focused on the satellite side of it, so how we track the fishing vessels to determine if they're fishing where they're supposed to, when they're supposed to, and how they're supposed to. So before we get into how we monitor IUU fishing, I think it's important to talk about why we monitor it. So roughly 25% of the fish on the market come through IUU fishing activities, so the fish themselves being illegally caught. That has an effect on stock assessment modeling, and of course, the depletion of the stock itself, because these fishing activities are not being reported as you would if you were fishing legally, of course. It also has an impact on the habitat itself. As we saw earlier, protecting marine protected areas is of high interest to all countries around the world that have any kind of marine megafauna in their area. And it's important that we not allow fishing to happen in those areas illegally, more so than any other reason. IUU fishing also has an impact on local fisheries in areas where an entire economy may be based off of artisanal fisheries. When you have IUU activities, typically those are well funded. They come in with larger vessels and deplete the stock that the local artisanal fisheries would otherwise catch, making it more difficult for those individuals to provide for their families and to catch the fish that they've historically been able to catch. So that's the why. Let's jump on to the how. So we are, if I'm not mistaken, the largest VMS manufacturer globally, and certainly here in the US, we provide VMS services for the Gulf of Mexico, New England waters, Pacific Islands, and the Pacific coast as well. And VMS systems are truly the best way to monitor a fishing vessel at sea, one that wants to have a VMS, let's say. So VMS has been around since the 1990s, and it's, put simply, it's a beacon that's attached to the vessel that transmits its information, its location every 30 to 60 minutes. And by doing so, it makes it very difficult for that to be hacked or spoofed as compared to AIS, which was discussed earlier, and I'll go into it briefly. But a VMS is attached to the boat. It's transmitting information every 30 to 60 minutes, and that information is the heading of the boat, its geo-positioned position, its speed, whether or not it's actively fishing or not fishing. So you're getting a complete picture of what each individual fishing vessel within a fleet or a fishery is doing. And that's a VMS in a nutshell. Some of the beacons you can see in the lower right-hand corner. One of them is ours, but there's, of course, other companies that make similar devices. And most of those, I should say also, they transmit through different satellite systems. Some of them use the Argos satellite system, whereas other ones use the Iridium satellite system. Just depend, and some use cellular as well for primarily, let's say, in the Gulf of Mexico, on smaller vessels that can't or are not interested in mounting a large VMS beacon. For a size reference, for those not familiar, let's say a VMS beacon's roughly the size of your head, footprint-wise, for a regular fishing vessel. So it's kind of the pathway that the data flow goes through the satellite system. So it goes from the beacon on the actual vessel, whether it's cellular or satellite, it goes through a VMS service provider, and then that data is then transmitted or sent to the National Fisheries Monitoring Centers, who then share it with the coastal states or local RFMO, Regional Fisheries Management Office organization. So in addition to VMS, we've coupled that with electronic reporting. So historically, you didn't see the data of what a vessel caught until it's landed at port, whereas now with electronic reporting, you can get that information in real time so that you can have actionable situations for, let's say, time area closures, or so that the fishery itself just understands a better, or has a better understanding of when they're catching fish and where they're catching fish to better allow them to have that resource going forward. So that's being adopted primarily here in the US and the European Union. And now just briefly on AIS, I'm not going to go into all of this, but to compare AIS to VMS, AIS was developed as a vehicle avoidance system. So my boat doesn't hit your boat. It's not really, it wasn't developed as a tool for IUU fishing activities. However, it has since been used as such. But with AIS, you can very easily hack your location, spoof your actual location, turn it off. Whereas with VMS, if you tried to do that same thing, because it's managed by a regulatory agency, they see you do that, and chances are you're going to get caught. So fortunately, Peter just gave an explanation of satellite imagery, which is something I'm least familiar with, but I will show you some pictures, and we'll see. We'll put Peter to the test when we get to the radar side, see if he can tell us what the little boxes mean. So there's two different types of satellite imagery that we use at CLS. We use optical imagery. We're all familiar with that. If you use Google Maps or anything where you have a satellite image, that's optical imagery. And here's an example of a picture that was taken showing a boat and various other vessels up next to it, either unloading or loading contraband onto it. So just some more examples of the satellites that provide optical imagery. Some of them will orbit every day. Some of them take, let's say, up to almost 2 weeks. So it gives you an idea of the frequency of coverage that you can get through optical satellites. There's a lot more, but these are just some of the ones that we use. And this is the test for Peter to tell me what I'm looking at, because I have absolutely no idea. But he did a good job explaining the difference, really, or the advantage of radar versus optical. You can use radar at night. You can look through cloud cover. You can see whatever this is and send a higher resolution satellite to actually go in and paint a picture of what you're actually looking at, because I think I've stumped Peter. Stumped myself more than anyone. So just kind of a summary, there are different satellite tools that we use at CLS and at the Woods Hole Group. Between AIS, VMS, we look at satellite imagery, both optical and radar, to have a full picture of what's going on in a particular area. Because while we do outfit a lot of fishing vessels with VMS systems, chances are they're not the ones that are doing the legal fishing because they're regulated by their states or by a country. Most of it happens illegally, and we use the other tools like AIS and satellite and optical imagery to catch them. That's all I got, short talk, and that's it. So.
Maybe you can stay here. Have two microphones here, and then so we have some time, and 20 minutes or so taking some questions to any of the three speakers. Have two microphones.
They have cooties, so I'm over here.
Hi, thank you. Thank you all for the presentation. Super interesting stuff. I was wondering if you could comment or just what the capacity is for these instruments to detect the kind of labor slavery issues. Like, are there vessel behaviors that, there are certain ports or just, I've learned a lot about it very recently. There's been a lot of coverage of the modern slavery issue and whether these tools are able to help us detect and respond to that.
I think Peter might be a good one for this because he knows more about satellite imagery, at least than myself. But I think that's primarily one of the indicators is use some kind of imaging system, because having a beacon on the boat isn't going to indicate that information, but having satellite imagery certainly would. Or like you said, maybe there's certain patterns of the vessels and their activities that would otherwise indicate that maybe they're not fishing or transporting cargo, but rather humans. But yeah.
There we go. Can you hear? Yeah, I guess from my perspective, I think one of the things that these slave ships often do is, they'll rendezvous with other ships. I believe that they often try to keep, the ships that are holding human slaves out at sea for a long time. And so then they, when they're catching fish, then they offload them to another ship, and that's the ship that brings it back to port. So I think there's a certain level of, if you're able to really monitor, and catch ships in this act of rendezvousing, and, then track back, okay, so these are the ships that are going to port, and kind of follow these behaviors. It does take a pretty high level of, of resolving what these ships are doing, their behaviors. It's not, you're probably not going to catch it in a single image. You have to be tracking and paying attention. So it's a tough problem, but I think, as more and more sensors come online and the data gets richer, I think there's more room to address it. But I don't understand this side of the issue too well. Yeah.
Okay. Any other question?
Yeah, thanks. Wondering if you guys could tell us how much do we know right now about the oceans and fisheries? Like, are we tracking most of the fishing vessels now? Do we have half of them? What level of accuracy, what kind of picture do we have day to day, what's going on based on what we have now?
Speaking to North America, I mean, we're really quite regulated. So in North America, I think we're doing a really good job of it. Unfortunately, that's the only area that the Woods Hole Group covers. CLS as a whole, I mean, we have 30-something offices around the world, and we have fisheries centers around the world too. I should say our other offices around the world are primarily there. We're built to build VMS centers in those particular countries. But in North America, I mean, we're doing a good job of it. In other countries where it's less policed, for example, I would say we know very little, generally speaking.
Go ahead.
Yeah, I would agree. Like, I think, at least in some parts of the world, like it's incredibly difficult to get a good picture. They're small boats, they're poor boats, and this kind of the regulations are much less and not enforced. We definitely do know of some pretty famous cases where you have huge fishing fleets that are everybody knows that they're doing illegal activities, that they're just infringing on the borders and turning off their AIS and fishing in places where they're not supposed to. So there are some pretty well-known cases of that, but I think just a lot of the smaller fishing that's happening all around the world. That I don't really know the statistics, but my feeling is it's really hard to track.
Maybe just to follow up, how long will it be until we have a really good picture? It just seems like there's a lot of technology going into sensing. At some point, shouldn't we be able to know what's going on even out in the high seas? How long do you guys predict that would be?
I'd say it's a challenge, right? Because I think the bigger issue, at least in my opinion, is addressing it from the port's perspective, from landing the catch perspective, and from the regulations within the countries that are impacted by it. I think that's where we should, as let's say a civilization or whatever you want to call us, address first, rather than trying to catch them. Just let's maybe better regulate them.
Yeah, I'd say it's obviously a huge challenge. And going back to the slide you showed, Thomas, that I think about 30% of fish is caught illegally, and the type of impact that has. And the reality is that oceans cover 70% of our land, and monitoring that adequately is very challenging. And obviously there's been huge technology advancements in what we can monitor from space, but there's still all kinds of small fishing boats that aren't going to be detected. And I think we need to continue to advance technologies to have more sensing, and that's part of what we're doing with USVs. So you have different ways of detecting things that can't be detected by satellites or not as well, and then fusing those data sources. So it's a very comprehensive picture that's going to need a lot of different solutions.
Yeah, and I guess there's definitely the willpower issue. Like, to some extent, we can put satellites up there that will have better temporal resolution and better spatial resolution, but certainly having other solutions on the ground, like USVs or things like that can. It definitely takes the willpower of a nation to say, like, we really care about protecting our waters and protecting our fish.
So I think the enforcement side of it is that's the challenging part too, right? Like you may be able to capture an illegal event, but to actually get that event enforced is hit or miss in some cases.
Yeah, and it's good to point out, like, it's super expensive, right? Like, if these illegal events are happening way offshore, are you, because you detect a ship fishing illegally way out there, are you going to send a Navy ship out there to address it? Or do you call for more information? At what point are you going to intervene, and how?
Right.
Yeah.
And I'd say at least sorry to keep
That's
interrupting
okay.
you. But the situations that I've experienced myself, or at least seen myself in exactly following up on what Peter said, is by the time they get to enforcing it, they're usually waiting until the boat is at dock. And in some cases, that's far too late. I was on a boat one time where that was the situation. None of us knew what was going on. It was with the National Museum of China, and there was about 20 of us ignorant people on the boat because we were going out there to conduct science. But the boat decided that they would line illegally caught mollusk, some kind of mollusk on the boat, cover it with all the science stuff, and they allegedly knew, the government of China, knew about what was going on beforehand, but didn't address it until we got to port, and a lot of us had no idea what was going on until 3 or 4 Navy boats came up and tied up to us, and then they started moving stuff, and there was just piles and piles of this illegally caught, shellfish or something.
My take-home message is challenging problem. The more technology innovation, more in situ platforms.
So I have 2 questions. One, I think, very short. And for the SAR, you said, I think, that it finds wake. So if a vessel isn't moving or it doesn't have any wake, do you not find it with SAR?
Well, I think that's just one use case. So, I mean, you can detect a vessel that's not moving. If it's big enough, it'll just reflect right off the vessel, and you'll pick it up as a bright point or bright points in the SAR image. But in some cases, like say a very small vessel can still leave a detectable wake. So it's just another modality where you can detect or reinforce what you're seeing, and also you might be able to derive heading information and that kind of thing from it.
So our company makes a very small vessel that can classify with cameras above water and acoustics below water. And so my question to you is how important is the ability to be able to prosecute? Because obviously finding them is frankly easy. It's what do you do? I mean, in your case, you were there and the Navy decided to come and pick them up for whatever reason, political reason or otherwise. But like I was talking with people from Kenya, and they said, okay, we know there are people fishing. People tell us, where they are, but we have no way to prove. They just say they drifted in. So how important is having actual on the ground or on the water evidence, do you think, in terms of really trying to stop this scourge, because you can prosecute with some kind of evidence?
Like how I do that?
Yeah, I don't know too much about that side, the regulatory side. I mean, I'm sure it differs so much country to country. There are a few stories I've heard about where really deterrence is a huge factor, that as soon as it becomes evident that the country is pursuing prosecution, and you just start taking a few ships to court, then that's a pretty effective deterrence for them to say, like, oh, we better start paying attention because we're being watched. So I think deterrence is part of it, but it's a good question, like what level of evidence is needed to prosecute, is needed to effectively prosecute, and how that's gathered. I'm sure that varies nation to nation.
And maybe I can just add on to that. I mean, from a USV perspective, I don't think any remotely collected data has been used for illegal fishing prosecution yet, at least not from an autonomous platform like ours. But I think imagery, localizing it to that region with geolocation or radar, ways in which evidence has traditionally been used to prosecute against illegal fishing, being able to provide that information using new technologies, is important.
My question's on traceability and just how this technology can really trace a fish from the wild to a plate. And I know that's a really challenging process because you can catch it one place and a country is of they're flying a flag of a different country and they have crew of a different country, and then they're sent to a refrigerated vessel out at sea. So I was wondering just how can this technology be used to trace fish from ocean to plate?
Wow.
Great question.
Yeah.
I don't know if trying to answer that is going to do me any justice or not, but I agree that's obviously very challenging how it's done in other industries. They'll attach small pit tags like you would have in your cat or dog with the little wand, and you say, oh, that's Fido because he got lost in the bushes, and now you have to pick him up from the humane shelter, right? So they do that with fish in some applications, but if we're talking about illegal fishing, I would just as well think that putting myself in the shoes of an illegal fisherman, I'm going to do everything I can to make sure you can't trace that fish. And from satellite technology's perspective, I'm not entirely sure how you would do that through satellite technologies myself. So,
yeah, I think, again, as our time resolution of what the ships are doing out there becomes better and better, we can start to form more of a picture of, okay, this is the actual ship track, what it's done. You can resolve, okay, there was a rendezvous, and you can start to form a pathway or a tentative story of what's happened. But again, I think that's really hard to, and it's happening so broadly around the world, to say that you're going to just be able to form that story right away is, it's a ways off, I think.
I think we still fall back on the regulation side of it, the regulation, the prosecution side of it. A lot of this happens in countries where there isn't a whole lot of regulation and very little enforcement. And when there is enforcement, in some cases there's bribery involved and other things to prevent that from even being reported. And I think that's a bunch of challenges that have to be addressed as a society, more so than maybe by technology itself.
Any other questions?
I was going to ask Julie, the Daphne also has sensors, right, to measure temperature and chlorophyll.
Sorry, what did?
Oh, I thought you mentioned, I thought in your presentation.
Data store,
Yeah, yeah. So how do we get that data? Where is that archived anywhere, accessible for studies?
Yeah, so we have that information. It's stored in our online portal. We collect it when we run missions for customers. So sometimes customers own that data. For the most part, we still own it. So yeah, we have.
Would you like to donate that information? No, after a certain time, maybe if it's more than a year old, you might want to donate it to NOAA and we can store it.
I think that's a great point. And this data that is collected, it should go to, it should be used to improve our understanding of the oceans. And if there's ways that we can support that, very happy to look into that. Thank you.
That's a great question. Just follow up. Can you comment about the value of data? I know is customer pay for it is very valuable to them. And then as time goes, maybe I assume the value will decrease. And then at some point, it may not be sufficient reason to monetize, so you can donate to public source, or open source, or another kind of public. So can you comment on how do you see that value decreasing?
So I think, as a USV platform, we collect a lot of proprietary data in places that there might not be another vessel collecting it there. So we're definitely, thinking about how can we use that to improve our own operations, improve our ability to detect vessels, but then also how can that provide some additional insights? How can it be fused with other data sets? How can it complement that data to provide value? So I think, there definitely is the idea that at some point in the future we'll be able to draw more value out of the ocean data that's collected. Right now, our business model is very bespoke services. A customer wants a data set, we go collect that. And of course, if that data can be used for other applications, whether it can be used to, advance science, or whether we can use it to make a data product, or whether we can use it to sell to another customer. and I think we should be looking at how this data can all be used and working collaboratively to fuse data together and make it more, interchangeable.
Julie, I have a question on your boat, and then can you say something about your future plan to scale up your vessel in terms of size, more batteries, or even hybrid power to provide sufficient power for power-hungry sensors and emissions?
Yeah, absolutely. Right now our vessel is a relatively small, low-powered, slow vessel that can be. The goal is to be able to produce it en masse and to be able to get them out there in fleets, to affordably monitor the ocean. But a lot is the sensors. They need more power. The vessel needs to be out there longer. So right now we're funded to build a larger vessel, which will be a hybrid vessel. So that'll allow us to go at faster speeds, to run some higher powered, larger sensor payloads, and also to go in conditions where the solar is less optimal. So more in the shoulder seasons, more in northern latitudes.
I have a question for Julie. So with the USVs carrying hydrophones and passive acoustic recording or monitors ways to do recording, have you also looked at implementing some intelligence that will allow you to determine if the boat is a fishing boat or if it's a cargo ship or something like this to proactively report that information?
Yeah, so we've run acoustic processors from other companies. So for example, we've run JASCO Applied Sciences, their Ocean Observer, which does real-time marine mammal detections. So we haven't not developed the software ourselves to do those detections. We can record acoustics, and then, if we have a communication method, stream it to a portal, and then analysis could be done there. But we, as a platform, we're very capable in recording passive acoustic data and doing processing. So, that's something that we're definitely very interested in, and probably really would look to a partner who has that ability to do those vessel detections. But that is a powerful combination where you're fusing data from multiple sources to identify and detect vessels.
Very good. We have 2 more minutes. And any burning last question to the 3 speakers? Otherwise,
I have another question. I was wondering how this technology fits into the U.S.'s seafood import monitoring program, and or any other international policies that are trying to fight IUU fishing.
I know they utilize the information from VMS to monitor where the fishing vessels are, and that trickles down through the catch that they have, and of course that's used for like seafood watch, for example. But beyond that, I'm not entirely sure. Good question. Great questions. Keep them coming.
Quick remark?
I was going to say we're usually interacting much more with the Canadian government, and have been interacting with Canadian fisheries for monitoring. But yeah, I don't know specifically about the U.S. policies or things like that.
Okay, with that, thank you very much. Okay, let's move on to the next panel, satellite application, marine litter pollutions. So we have first speaker, Vincent, CEO from Ethics. And then Vincent have been working there 10 years in France. Welcome. Specialized GIS software, global geospatial solutions. Floor is yours.
Is it a break right now?
I'm sorry?
Is it a break right
No,
now?
no, sorry.
I think everyone.
I think we have a break until 2:15.
Do we have a break?
Yeah.
Okay.
Yeah.
Really?
Yeah, that's why everybody left.
We thought to have a break afterwards.
Let me check. So
the break is after.
It's 2 and then oh you're right. Oh wait, that's weird.
Break at 3.
Oh, break at 3.
Yeah.
Oh, you're right. Okay.
No break? No break.
No break.
Break is 3 o'clock. We only have one panel. You want a break already? Maybe we can.
You're right. There's no break.
Right?
There's no break.
Break at 3 o'clock.
Yeah, you're right. Yeah, no, you're right.
Okay.
There's no
Okay.
break. That's why I read it.
I saw my senior. I already have a senior moment already. Okay, sit down.
He is like a long
Come on in. Yes. Welcome to the next panel, panel 4. We will get started with the next panel. Okay, get a coffee. Just give 1 or 2 minutes. People want to grab a coffee, so.
Hello, everybody. Today I will present a project. The project is called OPAT, for Ocean Plastic Alert and Tracking System. We are not tracking fishermen. We are only tracking plastic on the ocean. So just one word about Geomatis. Geomatis is a French SME specialized in geospatial information system development, really focused on standards and geospatial standards. We are a member of Open Geospatial Consortium, and we are promoting interoperability in our systems. So we are here since more than 17 years now, and we have developed a software universe dedicated to process every kind of geospatial information, satellite imagery, sensor observations, and so on. And more recently, about less than 10 years ago, we decided to work on big data analysis, and more specifically on the Earth observation domain. So 4 years ago, usually we are developing system for other company and big company and or institute. For example, we are working for French Space Agency, Japanese Space Agency, European Space Agency. We are working for naval industry and French Marine. and so on. And more recently, we decided to develop end-to-end projects. One called EpiWise for epidemiology. Logo, it's water quality monitoring, and OPAT for tracking plastic on the ocean. As everybody knows, there are a lot of plastic in the oceans, and the problem is not resolved for many years. We are good in processing data to identify some information on it, and we decide to start using open data satellite imagery to see if we can find some marine litter or different kind of objects that are floating on the oceans. For that, we won funding from CNES and European Space Agency to prove the feasibility of the plastic detection on the ocean at different resolutions. So detecting plastic on the ocean is not an easy task because there are big dump of waste that are floating. It's easy to detect because satellite can the satellite resolution of, for example, Sentinel-2 optical satellite can detect big piece of plastic on the ocean, but when you want to detect small packet of plastic, it's more difficult. So optical imagery is not enough to detect plastic. So, and we have to find other way to identify where the plastic is. So we decided to look at different oceanic phenomenon like sea currents and so on to forecast where there are plastic aggregation. So for that we have to process a lot of data. We have to drill down a temporal series of satellite images. We have to do data fusion between moving feature and environmental data provided by satellites. So we have developed this solution which is a connector for data lakes and which simplify data management for the data scientist community in order to develop new algorithm to do the detection. So one other problem is the temporal resolution of satellites, even commercial satellites. For example, with Sentinel-2, which has a temporal resolution of five days, you have to follow the drift of the plastic during those 5 days, and after 5 days, if there are clouds with optical satellites, you can't see where the plastic is. So we have to work on different kind of solution to track the plastic. Here we have developed. We are forecasting the drift of plastic and verifying after a period if the plastic is still there or if the plastic is at the position we forecast it. So, sorry. Okay. So the feasibility is one thing, but one of the point we have to address, one other point we have to address is economic credibility of the project. Detecting plastic, it's okay. We can do that, more especially for big climatic events where there are floods and hurricane and so on. There is a lot of big aggregates of plastics that are arriving near the shore. But if there is no economic model to pay for the detection, it's useless. So we have identified different stakeholders, and for example, the touristic towns that are near the coastline, they have to keep the beach clean, and it costs a lot of money. Cleaning the beach with cleaning the beach on the beach itself means you have to wash the plastic after to extract sand of the plastic in order to be able to recycle it. So it's a lot of work, and economically it's not really good. And catching the plastic directly on the ocean is a good point, because the plastic is clean when you get it. So we started to work with some city of the French Basque Country, because the French Basque Country 20 years ago was totally flooded by an ocean of plastic coming from huge waste dump in Spain, which was near the ocean, and they decided to pay fishermen during the touristic season to track marine litter and to catch it before it go on the beach. So they were really interested, because the boat is navigating randomly, and by chance he can catch some plastic, but sometimes he catch nothing. And if we are able to give them tracking system, they can be more efficient in the way they are getting plastic, and they are consuming less fuel, so it's more green for the city. So another motivation was this big meteorological event. In the south of France, we have such kind of event. For example, in autumn, there are a lot of rain and a lot of flood. And at that time, a lot of plastic coming from the ground is coming to the sea and is aggregating in big packets. So if we are able to detect this packet of plastic, then the cleaning of the coast will be more efficient. So this is just something we have done quickly before coming here. We have processed Sentinel-2 images around Florida after Ian hurricane, and the zooming process is not really good, but we have easily detected some really big big packet of plastic here. So now the goal is to we are able to detect big big packet of plastic, but now we have to test for other kind of sensors. For example, SAR, which is really useful when there are clouds, of course. But SAR is the SAR resolution is not really good to detect small amount of marine litter, and perhaps what we are looking at is when plastic is drifting since a long time, on the ocean. A lot of algae are developing on plastic, and the surface of the ocean at that place is modified, and then with SAR, when processing SAR, we are able to detect, but it's really it's not really accurate, but we are able to detect some plastic. So what our goal is to we want to develop this project in different way. Of course, for local authorities, like I explained, we want to talk with company who collect waste and who transform plastic in order to create a value chain that could be useful for the economic credibility of the project. And then we are starting to look at different kind of customers for this system. So that's it.
Thank you very much. We'll hold a question toward the end, so we'll move on to the second speaker.
Okay.
Is that okay?
Okay.
Yeah. So, do we, are you the next one?
I don't know. There's like 3, right?
Do we have Edward Swaz from here? So he's on here.
Sure.
So Maddie then. So Madeline Cowell is an engineer from Ball Aerospace. She's also a member of the International Committee of Marine Debris and specializing marine debris. Thank you.
Thank you. Yeah, so I am a representative of a larger task force and a steering committee that really kind of takes together different space agencies like the European Space Agency, NASA, and we have JAXA, and I believe the India Space Agency as well. And ultimately, we sit under the International Ocean Color Coordinating Group, which is a mouthful. And I'm going to say another mouthful, which is then we're the task force in the subgroup of really focused on remote sensing and marine litter and debris. So I guess I can do the next slide. So who are we? I think we don't necessarily have a solution, but really what I can offer is a network. And really what we're trying to do is connect a bunch of people of like-minded research to understand really what are the limitations and what are the gaps in which we can kind of use as a foundation to jump over hurdles. We really love coordinating. It's hard. Time zones are rough. I think we're a pretty strong force in Europe. We've got some US contingency, but you're also trying to loop in Hawaii. And so we do our best to get everybody included. But really, all of us seem to contribute in some way or form to the research. I think really we're a bunch of scientists and researchers who are looking to see what potential there are in the technologies and figuring out what kind of roadmap could we maybe develop to help kind of answer these questions of, where is the litter and what can we do about it? So just a little bit of history. I think this field is relatively new, and it always blows my mind with how quickly we've been researching and contributing to the world of science. And ultimately, it all started On remote sensing specifically, I shouldn't say all plastic research started in 2016, but when it came to remote sensing and understanding what could we do with sensors, it really started in 2016 at the University of Hawaii, led by Nikolai Maximenko, who's a modeler and really is interested in understanding the transport of the debris. Oh, I didn't realize I was pushing buttons. Since then, we have had multiple workshops. The European Space Agency, I think, took up the next torch and really kind of continued to cultivate the community. And then since then, we've really started to see funding opportunities in the space agencies themselves. ESA being one, NASA, which I can say thanks to because that's how my research is funded, and the Portugal Space Agency has also shown some projects through funding. So the task force contributions, just over the last year, we've been at a bunch of different events. I'm excited to be here representing just another way for us to try to get out in the community to say that we exist. Kind of the most notable that most recently happened was the UN Ocean Conference in Lisbon, Portugal, where we talked about an integrating marine observing debris system, and then also the 7th International Marine Debris Conference, which was in Korea. So ultimately how we've structured ourselves, we're in 4 different core topics. We have our technologies, then we have our algorithms. You can't do anything about algorithms unless you have data, and then ultimately we have our interdisciplinary aspects. I lead the core topic 4, so trying to engage, get people to know about us, and talk about, I swear I didn't touch it. Oh, is it on? It's probably, I'm going to keep having to touch things then. So in terms of, we have our CT1 leader, which is Victor out of Plymouth Marine Laboratory. He is leading a group to really understand what is current and what is emerging in terms of technology itself and understanding the gaps and opportunities. Algorithms, it's really understanding, our state of the art. That's led by Manuel, is in our core topic 2. Really, it's like, okay, once you have this data and you've collected all these photons, what do you do with those photons? How do we actually say what's of importance? And then data sets, I think that's one of the biggest challenges, is that remote sensing has tons of data and tons of history, but when it comes to validated data, the data that you need to actually say something about what's been collected is very scarce. And so we're always trying to understand what are the needs in this section and how can we help generate or push for more data and really make it open access. So in terms of our technologies of interest, we've heard a lot today about the optical remote sensing, so multispectral and hyperspectral. Really what we're interested in is in the near to the SWIR, shortwave infrared. There's some really great polymer features from thinking about like how you could distinguish from something like phytoplankton. We're excited, actually I should say, I'm really excited about the laser base, so thinking about ocean LiDAR and understanding what could the backscatter return, what could fluorescence return look like, and kind of how could we maybe ID and do a signature off of that end. There's also, I should say the depth is very deep on each of these topics. And then we also have our microwave based. And that one's really, again, SAR we've talked a lot about today as well, but really that surface roughness. Kind of some of the thoughts there is if you have a really large presence of plastics and you have wind events happening, it's actually that deviation of an expected dampening that might lead you to, beyond just surfactants, maybe microplastics, macroplastics could be contributing to the signal. And then all of that has to be in concert with the retrieval algorithms and making sure that we understand the state of the science. Really any platform, as long as we're not maybe in the water or doing point samples, is what we're interested in. So whether it's shipborne, drones, ultimately getting up to satellites is kind of the, I wouldn't say the holy grail, but a really exciting piece of the puzzle because it really does give you that global coverage so that you can start to do a true global budget instead of just localized regional studies. Oh, I went backwards. So ultimately, the kind of applications we're trying to target is we want to be able to detect, just say, is it there, is it not? We really would love to identify what kind of plastics, I mean, beyond just what sits at the surface due to densities versus what sinks, I think we could maybe infer what type of polymers are at the top. But ultimately, it would be nice to be able to bring it so that we knew what the sources were. It would be amazing then to get to quantifying. I think one of the big things is we keep hearing studies coming out about these are the estimates that we're dumping into the ocean. But right now trying to close that budget is really challenging because we do have limited resources to go out and do point sampling. So getting to that quantify would be really huge. And then ultimately, now you've got all of this, you even want to start tracking it. And especially with the light of like the UN Ocean Decade, the newest plastic treaty that's been proposed, all of those different pieces are going to be informing policies, and we want to be able to understand how are we performing to those policies. But the biggest challenge is size and variety. I should say size though, right now with our current set of satellites and thinking about spatial resolution, you really need large aggregate data, as we saw earlier. It's one of the biggest challenges. We do have a scale limitation because we need enough accumulation for us to get a good signal off of it. Beyond that variety, I said that there are some great features out in the shortwave infrared. Shortwave infrared is notorious for being absorbed by water, so not a really great mix. And so it is still a challenge to understand, what kind of variety of debris are we really working with when we see these large accumulations. So ultimately, where we are today, I think a lot of people will agree aggregated plastic seems to be, where our eyes focus. But I think kind of going back to the purpose of this group, a lot of us are researching kind of what's coming up and the emerging technologies to come. So just to kind of do a really quick highlight of some of the activities from the different space agencies, ESA is just about to complete their campaign, the Discovery campaign, which is really like the first time, at least in my memory, of being excited about all the funding getting into the marine debris and remote sensing research. So really excited to see how everything will conclude. These are just some snapshots of the types of work that's being done. Anything from tanks in the lab, 2 planes, 2 large deployments. I swear I'm not touching it. And then also getting to the point where we're starting to model and understand the impact. And in terms of NASA activities, we've got the ROSES grant, which is kind of our major funding line. And so we had 3 different projects out of the ocean biology and biogeochemistry program. Nikolai Maximenko out in Hawaii, he's got a couple projects that are really leveraging citizen science out in Hawaii. And then I also have a project that's looking at fluorescent signatures off of plastics. And then in the Portugal Space Agency, I think really, again, it's complementary, thinking about how do we actually take a lot of the EO and optical sensors and take them out to the field, and then a lot of AI and algorithm development. Because again, it's great to have photons, but if you don't know what those photons are saying, it's really hard to disseminate the information. So ultimately, why I'm here is to tell you we exist. Our task force is trying to be a one-stop shop where we try to keep everything up to date. We've got a nice, upcoming events, research topics. And this is the slide I wanted to actually have the most static, because this is a QR code to scan to get to our website. Overall, we've been keeping like a bibliography that anybody can come in and use, as this is like the top hits for marine debris. We've got 81 peer-reviewed papers as of last month on our website. We've got 13 data sets that are available, so if people are interested in that. I'd like to do a quick plug though for Ocean Scan. That's an ESA-funded activity, and they're actually really trying to do that ground validation and provide an open data set for people to do machine learning and different types of algorithm training. And then ultimately we have tons of repositories linked, so we're really trying to be this place where you can come and start to do the learning journey, or if you're seasoned and expert and feel like you're missing, please let us know. We want to continue to grow the community, so we want to make sure your research is captured. So way forward. Ultimately, we're really trying to understand what the limitations are of the current technology and understanding what gaps we should pursue when it comes to emerging technologies. I think one of the big things is really trying to fuse all the different data sets being collected, anything from people sampling on the ground, trawling nets, cleanups. I mean, there's lots of opportunity for us to start collecting data, but there's no harmonization, and we're really trying to be in step with other organizations like IMDOS, which is the Integrated Marine Observing Debris System. And then ultimately, wasn't done yet, but we're really trying to get an idea of like, where are we going? And the biggest feedback is getting the stakeholders. I think it is very similar to the IUU talk in the sense, it's great we can detect it, we can find it, but now what? And I think that's really the missing link in terms of turning on funding and saying, this is why you should fund these projects. So if you know anybody who is really passionate about this and has maybe pockets, it would be great to have the conversation to understand what data you really need in your hands so that we can continue to inform the research. And so with that, I think I'm going the wrong way. Thank you.
Thank you very much. So I have yeah, you can sit down. We have 2 microphones, I guess. So, you know, we can have Q&A. I first want to tell you the bad news. So the first speaker I'm looking for, I just checked my notes. The program changing dynamically, and from Germany, he was not able to come because of emergency reasons. So that's a bad news. If you know, we are missing 1 talk in this panel, but the good news is we have more time to ask the 2 speakers here, and also to discuss any topic you may be interested. So who want to ask the first question?
Can I actually make a quick note? I forgot to say core topic 3, leader Shamgu Garaba. I was just going through my head and saying, oh, I think I missed someone, so I just wanted to make sure his name was out there as he's on the task force.
Yeah, I think Nikolai from Hawaii moved your slides. So
yes.
Yeah, I'm pretty sure. He's a good friend of mine.
Oh, good.
Any questions? Go ahead.
So for the French example where the fishermen were going out and collecting the plastic, I was just curious, how do they make sure people don't game the system and say, oh, I collected this plastic, but they really just got it from, you know, from their own recycle bin? For the fishermen that were being paid to collect plastic from the ocean, how do they make sure people aren't, you know, taking advantage of the system and just taking plastic from, you know,
from the neighbor?
Yeah, from the neighbor and saying we collected.
Yes. For the Basque Country, it's a bit, the fisherman was excuse me, for the Basque Country, the fisherman was about to retire, and they employ it to do the job, but he doesn't have nothing to gain when keeping or not some plastic. But what's really interesting with this project is that the fisherman do it for about 10 years, and after his son now is doing the same thing after him, and we have 20 years of data about what they have collected. So that's the interesting part of the project, is that we now we are able to verify on the field, to have field verification of what we can look on satellite images, and what is more difficult is at the beginning the fisherman was not pointing the place where the plastic was. So we have to look at the pattern of the trajectory of the boat to identify where he was picking some plastic. But after that, after processing the data set, we now have a database of where some plastic was, and we can get some satellite images, old historical satellite images, to train our algorithm to detect even Landsat images, spot images, and so on, historical spot images, which are free right now. And so this is an interesting part of the project. But of course, if paying fishermen to grab some plastic on the ocean is something that towns want to do, because it's less expensive to pay a fisherman than to buy a boat and pay people for the season to do the job. And of course, after that, we have to verify if the plastic is real marine litter or not, but that's another problem.
It's a great question. I don't think I know the answer, but I run into another company in the Bay Area a couple of years ago. It's not tracking plastic, tracking kind of fish, and then the good part, basically by analyzing the materials in the air, and they can track where, they can fingerprint where they come from particular continent, from the countries. It's like a device, basically like a fingerprinting by saying, I'm exposed this area in Indonesia, in Bali or something, and then moving through Japan. And so they will be able to fingerprint just by tracking through the air exposure. I think they talk about tuna or fish or something, so seafood from the ship to the table, they can plot the trajectory. This is like a few years ago. I don't know whether that's become a unicorn or bankrupt, or I don't know. I even don't remember the name. But there are companies developing that kind of tracking technology. I think for ocean, the environmental analysis probably eventually will catch up to analyze, here's the water, here's different type of water, and here's on the boats, and then track them, right? So I think earlier panel, technology innovation probably will help to address that question. So, any other question?
So I tried to do some satellite work on plastics a long time ago in my PhD. I think it was like 2014. And one of the problems we had is that the best satellite data is really on land and near shore, and like out in the open ocean, the satellite paths just kind of skipped it. And we really care about the middle of the Pacific Ocean, and most satellites just really skipped that. So do you have big empty spaces in your data sets, or have you been able to kind of find that data?
No, you are hitting the problem that we have when it comes to trying to understand the open ocean problem. I think floating plastics is really our best bet, so that actually also limits the number of polymers that you can see. And you're absolutely right. The Landsats, the Sentinel-2, those are definitely made for land imaging. And so when we try to repurpose it, that's awesome. But the signal, the ocean's really dark. And also that dynamic range to go from dark ocean to the land is also another challenge. So in terms of we are scarce on data. When I say that, it is, we're looking for things off of coastlines and trying to understand, okay, now that we know these things off of coastlines, there is actually, since 2014, and I'm sorry that you missed this window, but ESA did actually open up Sentinel-2 to collect over the southern part of the North Pacific garbage patch, if I remember correctly. And so they just opened it up for a brief period of time because as it is, I know Landsat probably better than I do Sentinel-2 just based on where I sit, but I do know there's a lot of concern and risk that when you start to, turn the satellite on in places it wasn't planning on operating, you have to convince a lot of people that that's a good idea. So in terms of, I know we're trying to leverage opportunities like that and get really deep into the data, but it's a really challenging problem because beyond just even the sparseness of the data, with our sentinels and worldviews, we really love those near infrared and those SWIR bands, and sometimes we'll use information from the red, green, blue. Those are all at different spatial resolutions. So you're now also trying to understand, okay, well, if I've got 10 meter resolution in my VIS and I've got 20 nanometer resolution in my SWIR, what am I really saying about, what's in between? So yeah, it's not easy. And I think that's why I think we get so excited about the emerging technologies. I feel like we're really trying to push the current constellation to its edge. And we're trying to squeeze every ounce out of it. But when you're talking about open ocean versus coastal zones versus terrestrial accumulation zones, I think they currently all look different. And so I know there's a lot of people who are interested in, well, what does a unified plastic sat look like? And so I think I'm really excited to see where this future kind of goes, but I do really think we need to nail down the application. Just because we can build it doesn't mean we should. So I think that's been the biggest barrier, is making sure that we're all on board with the same desires. That was a long-winded answer.
That was great. That was great. Okay, I'll ask another question. I don't see any hands. Speaking of pushing it to the edge, what is like the smallest size range of plastic that you guys can analyze?
So I'm actually maybe going to phone a friend with Mitch. If worldview spatial resolution, is that a meter? 3?
No, they're down to a meter.
They are down to a meter or 2?
Yeah,
25 centimeter on like the panchromatic sharpened, right? Yes.
Yeah, but they don't gather data everywhere, right?
No, you have to task it. Yeah. So that would be the answer, is like that pixel is really going to determine what you can see from spatial, and relying on one pixel to give you enough information probably isn't enough, and you need multiple. So you start really building up. And I'd say with a lot of the free satellites, we're talking, it'd be great to see something 50 meters or more in a mat. But in terms of like thinking about the worldview, I know people have pushed it. I don't know the limit, but I do know that normally that spatial pixel resolution is the factor.
Okay.
Yeah.
Gotcha.
Kind of tied to that, and you hinted at just the conglomeration of plastics, how it can kind of change the nature of the sea surface. So does that, one thing I hear on the news all the time is the discussion of microplastics and the small things. Like, do those have any signature? Is there a path forward for tracking those?
Path forward, I won't necessarily speak to, but I can speak to how people have published work to maybe draw some conclusions of how you can use Cygnus data to do microplastic concentrations. And so that was a study out of the University of Michigan where I would say a lot of things still need to be understood. Like I mentioned, the surfactant factor of dampening your surface is definitely a big driver, and being able to decouple that from microplastics sounds like a pretty tough challenge, but I know that they're actively researching that. But really, when I've seen microplastics, it normally has to be into some comparison to a model that then takes another wind driving model to say it's the delta and the anomalies of interest that maybe gives me some hope that I'm seeing something of microplastics. So much more of a derivative measurement than a direct measurement, but that's at least my experience from satellites.
Yes, another point is hyperspectral imagery, which is really useful to detect what optical imagery or radar imagery is not able to detect. But there is not a lot of sensors in space right now.
Coming though, right?
But it's.
I heard that 10 years.
Yeah.
But it's something. I think really useful to enhance the model.
So just adding to Peter's comment, you're correct to point out a lot of the work currently is focused on patch plastic, large-scale plastic detection, and etc. But really, from previous work like Jenny's dissertation work and other folks, really the microplastic, almost to the dissolved micron level plastic is what's really impacting ecosystem and biogeochemistry. And we keep talking about spatial resolution and the detection limitation of satellite imagery. What about treating these microplastics like some of the other existing Earth observables, like treating it as SPM or treating it as particular organic carbon? So right, those things you can't detect by spatial resolution, but they have optical signatures collectively when they're concentrated. So has there been steps, or is IOCCG thinking about detecting microplastics from that approach?
I think we're always interested. Microplastics is something that I get really excited about, more because I think I've seen some really cool strides on going beyond just mantitrals and thinking about, that's how we do our accumulation for microplastic studies, because there's so much citizen science out there that people want to contribute. And so if we can give them ways to do microplastic sampling, we should be equipped to do so. So there's a lot of technology coming out of that. When it comes to satellites, I think one of the things that, sticks with me, and I might be misquoting, so please don't hold me against this, but the concentration itself, it's hard to know how it varies and what exactly is happening in order to probably process a signal. I think the microplastics question, it's so multifaceted and so tied to physical ocean dynamics that, and I have this fear of, it's been there for how long? So like really, how do you pull a signal out of something that probably already is just like kind of a basis, so almost like a bias? And I think we aren't quite ready to say anything on sensors, but I do think that there's a lot of work to be done about maybe trying to figure out how do we leverage other data sets that maybe studied phytoplankton or things that also are of scale, but maybe we weren't looking at the time, like in the 60s and the 70s. So trying to understand how can we start jigsawing that puzzle together, I think will then give us the opportunity to think about the future. Because I mean, I always think, oh, like what could LiDAR do? I mean, we talk about phytoplankton blooms and things along those lines, but again, because microplastics and the concentration is, sometimes as I'm told, like it's too little to do much, that yeah, I just don't know what we're gonna find. So stay tuned.
Hi, thanks. This is such an important topic. Thanks a lot for your talks. I'm wondering how much effort is being put into detecting the sources of the plastic pollution. And as difficult as it might be, would it be effective to create a database of every recycling center, every dump site, every, everywhere that plastic goes, every ship that transports it back and forth, and find those places where they're, because isn't that how it's really happening? It's from a concentrated source in a lot of ways, and then coming into the ocean and identifying those places and stopping the plastic there before it gets all the way out in the ocean for years and years and breaks down and becomes microplastic.
I can speak a little bit, but do you?
No, please.
Yeah, okay. I can talk for days on this topic. Yeah, I love thinking about our source and where things are coming from. So when I first entered this research, it was all about actually finding derelict fishing gear. Nylon was a really interesting polymer. Fun fact, it sinks. So that was a bummer. But in terms of like understanding its use case, it was clear like, oh, derelict fishing gears, that's a source. I can go to like the fishing. Thinking about tying into everybody else's conversation today with AIS and maritime awareness, it's amazing what we know there. But when it comes to like actually starting to shift the lens and looking upstream, I think there's a lot of anecdote and stories, but I haven't seen a really good resource, and maybe it's just I don't know how to find it, that says, this percentage to, I mean, we know what we consume, so that's always everybody's starting point. The U.S. consumes so much. I know we're in the top 3, I feel like, and then other countries contribute. Okay, so we know that the U.S. is the source, but we've heard anecdotally, we've shipped recycling out to China. China closed their doors and said, no, we're not accepting this anymore, and we tried to find other pathways to get the recycled goods elsewhere. And then it, got to the point where I've heard amazing, wild stories of people basically taking it to other countries who aren't necessarily equipped to handle all of our trash. They just go upstream, dump it, and then they kind of let it do the rest. And so I think some of the really cool efforts I've seen on trying to get this, it's almost an intelligence view on what is the supply chain of plastics on the back end. And it's the Minderoo Foundation out of Australia. They have a global plastic watch, and they actually use satellite imagery to find illegal dumping zones in Southeast Asia. Actually, and I think they've expanded it. I almost want to say I've seen something in South America, but it's been a bit since I've checked their website. And so they did the first attempt of showing like illegal dump sites. But then, there's lots of questions of, okay, let's just take the US as a use case. Recycling practices and methods vary state by state, city by city. It's like there's no real good standard way to tackle the problem just yet. And that's where I think I'm really lobbying for the policy side of it, the regulation. I know in the fishing talk prior to this, without regulation of saying this is how we should handle our waste, it's up for debate where it goes. And so it's such a large scope that I haven't seen good path forward. But it doesn't mean that it doesn't exist. And actually, maybe by me being here, we can get the maritime folks thinking, with things like AIS data and tracking shipping containers, and if my presence at least just gets that conversation going of thinking about the supply chain of things, I think that could be really powerful as a way to even talk about where do we need to look for remote sensing, tasking, going back to that, instead of just relying on 16 or 8-day revisits. So anyways. Long-winded.
Can I just follow up on that?
Yeah.
Couldn't you get a good handle on that with just 10 or maybe 100,000 sensors that you sneak into plastic all around the world and just throw it away? And
So there's some really cool, so Scripps actually did like a plastics challenge to the Rady Business School of saying like, oh, how do we, even tackle this problem? And one group of students actually said, well, I'm gonna put a bunch of sensors in my trash and figure out where everything goes. So like I've seen that kind of deployment before. I've also heard rumors, and the only reason I even got, fluorescence is a very interesting property of polymers, but Europe has even talked about, dyeing the polymers with a fluorescence dye so that it's easier for us to find or track or sort and things along those lines. So I know that there's conversations happening, but I haven't seen like a tops down, thou shall do this yet. And so I think the biggest hurdle to that, to make that happen, is the cost.
Yeah, but I think that's not that expensive. Like, that's within the realm of big grants or the Gates Foundation or something like that. Someone could do this in a year or two.
Yeah, so I have on two paths. On the grant side of things, when it comes to finding things you can apply to grants, especially marine debris, plastic pollution, there aren't large buckets of money. I have searched and I have tried to find government funding, so that's been tough. But then on the nonprofit side, nonprofits aren't necessarily interested yet. I think right now methane, greenhouse gases, all of that emission story is really dominating kind of where we're throwing our money. And I think plastic pollution is kind of just, it's wild how interconnected the two are in the thinking of like when we create these polymers, the emissions we dump into the atmosphere. Like it's a similar story to oil and gas, but it is very much behind in terms of funding. And actually, I do have one resource that maybe I can share to the Whova app that kind of does this tie of the cost of plastics, the cost of like how much are we actually funding it, and how far behind are we in the science. Yeah. Okay. Cool.
Can I follow up on that question? So the second C in the IOCCG is coordination, right? It's coordinating all the ocean color community. So, so what has been some of the efforts from that group to coordinate with Institute data? Because I think one of the big effort that should be, people should invest in is to do the matchup. I think there's enough satellite data. There needs to be more coordination efforts, more matchup between the satellite data and the Institute data. So that way, when we write algorithms, we can build better machine learning algorithms to detect, especially the microplastic component.
Yeah.
So what has been some of the efforts from that group? Because I'm not directly involved, I only read their reports and.
I feel like you are at the same seat that I'm at in the sense that so the IOCCG, the task force itself started in early 2021. I am new to the group, and it has been trying to go to conferences, to talks, and say, we're doing this. I think that's probably the biggest output we have right now, is that we've held a couple webinars where people can join in, but ultimately it's trying to find platforms to have these conversations and make sure people are actually talking. I think that's been the biggest hurdle, but I think at least what I find the most rewarding, and when I say, have I done something for IOCCG's task force, is, I've been trying to make those connections. I hear about, there's I hope he doesn't mind that I use him as this example, but Beckett out at Woods Hole Oceanographic Institute has a microplastic sensor that I think is really interesting based off of flow cytometry. I came across it at a conference at a poster, and all I can do is keep forwarding that paper. And I think really in terms of like when it comes to coordinating, especially internationally, especially when you're competing with policies and just like how people actually attack this problem, all we can do is just kind of accumulate the masses. And so I know my selfish plug, so I'm on the interdisciplinary side, and I want to see more workshops where we are trying to tie those user communities. I'm going to be applying for workshops and trying to get money so that we can actually have these conversations, try to write white papers to help inform the community. And so, yeah, but at the same time, because it's an international group, it's slow. It's not a team I can just walk down the hallway and say, we're doing this week. It's very much trying to make sure that we have the momentum going. And so, yeah, unfortunately, we can point to lots of things. I think Ocean Scan, in terms of validation data, is a fantastic platform where people have been uploading their research data points of like, hey, I went out, I threw out a target that was 10 meters by 10 meters in the Mediterranean. Here is the lat long, the day, and I used Prisma and Sentinel-2. And so that stuff is currently existing, but it's not owned by the IOCCG. It's kind of, we definitely are trying to make sure everybody's matching to it, and that's all we can do. But that's kind of probably the most coordinating output.
Let me follow up on that question. And a lot of this seem emerged the integration between satellite and in situ data. Satellite can see better and better, but it's always limited. So Mitch's presentation clearly showed the fusion many other speakers talk about. So if I have a hypothesis, let's say hypothetically, if we can send 1,000 boats Julie produced, just imagine, assuming she can produce 1,000 boats tomorrow, next year, and then we're keeping her busy, her team. What type of sensor and data, I want to ask two speakers, you would like to, money is not a limitation. What sensor and data you want to collect? One. Top.
One?
Mm-hmm. 1, 2, 3.
Okay. You can go first.
What data you meet your unmet need, solve your biggest problem? What's the top sensor? It's 2.
The top sensor?
Yeah, sensor and data.
It's you. It's you. It's you. If everybody can get my mobile phone application and can everybody on a boat see plastic and look, put a localization of the plastic and take a photo and take information about the plastic, we could have an incredible database to.
Okay, so you talk about people with
people. We are working. Geospatially speaking, we are working on sensors and moving feature and so on, and we are working on sensor systems, sensor platform, and so on. And for me, the best sensor is a human, because you have eyes, you have ears, you have everything you can test if you you can.
But for open ocean, what about a robotic? For example, in the open ocean, if we have a robotic platform in the middle of the ocean, people usually cannot go. What sensor come to your mind? Yeah.
Could I add something? I'm very sorry.
Yeah,
just to clarify, I think a better way to think about this, and I actually have an incentive to ask this question for another project. In addition to sensor, what do you want to measure? Do you want to count plastics? Do you want to count the quantity, volume? What's the observable that you are interested in?
Yeah, if you cannot come up with sensors, name a data set. Yeah. That's fine too.
Go, yeah, go.
Sorry.
What's interesting? It's a radiometry, the radiometric response of the plastic, but it's not the same when the plastic is young on the ocean and when it's old and so on. So that's why if you detect some plastic and you take a photo and you just enhance some information, metadata, and you put it on the global system, it could be helpful to train, for example, a deep learning algorithm to automatically identify what could be plastic on an image that you, or for example, to identify when sense an image from combined with another image and so on could give some a combination of response that could match with presence of plastic.
Sorry to cut you. It's optical imager, so go
ahead. So my head spins when I get that. I'm going to pretend like I have the perfect sensor, and that sensor is going to be able to tell me concentration.
Concentration.
And so what I would love to see is something that sits at river mouths. And then what I would love to see out in the open ocean profiling, like I keep thinking, how can we leverage the Argo data set? I would love to see what's going on in the water column. I think lots of interesting hypotheses around like, oh, it's settling at the mixed layer depth, or it's getting all the way down to the surf, or it's down to the bottom. I think it's so unknown and so hard to capture that. If you had a bunch of autonomous vehicles out there doing one mission, I think that would be what I'd love to see, is understanding the transport of these things. Because maybe we don't need a satellite. Maybe we just need something that's looking at a river.
Complementary.
Exactly.
You need both.
Yeah.
So
yeah.
Julie, take notes. You need to dive your boat.
Yeah. Yes. Well, I hate to be the person to make a comment and not a question, but I would say 90% of the plastic is smaller than what your cell phone camera can take a picture of. So I think it's important. I think satellite images of the big stuff is really important. I think camera images and images off ROVs are really important, but I think it's also really important for us to make sure we are doing sensors of the really small particulate matter stuff, because that is actually numerically the vast majority of the plastic in the ocean is really, really small. And I'm not sure the perfect sensor exists yet. And I think a lot of people are developing it, but I don't really think it's out there yet autonomously. And that's why it takes so long for us to analyze our samples, because we have to do it by hand.
Yeah, really, sorry I have to cut it off. It's really exciting. I want to keep talking. You know, this is a really great topic and good interaction. We have a coffee break right now. The panel right after the coffee break is empty, so there's a speaker we're not able to attend. So we have an open slot. I ask people to submit questions. Another way we can have an interactive discussion on any topic. Maybe the audience can introduce themselves in a couple of sentences, what they're doing, and know each other better. The problem with this conference, you meet a lot of people, you have a hard time to know what they're doing. So give everybody an opportunity. We do have 45 minutes available in between before the final panel. We'll talk about sea level rise. So we'll take a coffee break, think about the questions, and then come back 3:15, 3:20. We're going to have open discussion, introduction, debate, hypothesis, testing, whatever you want to do. Thank you. for coming back for this session. We're using this microphone because people online will watch them, so we try to talk to the microphone and so the people online can see it. So we have another session before the networking break, talk about sea level rise. So Ben will kick off the first talk from the space perspective, and then Professor Mark Merrifield from Scripps will talk about in situ sea level rise and coastal impact adaptation. Ben, floor is yours.
All right, thanks. All right, so thanks for the introduction. I'm a research scientist at the NASA Jet Propulsion Laboratory. I'm team lead of the NASA Sea Level Change Team, so kind of look broadly at sea level using satellites and trying to solve a number of problems. But today I'm going to talk specifically about the satellite observations of sea level that we have. And as with any good talk, I'm going to start with social media disinformation. So at JPL, we get regular requests from reporters who see something on, say, Facebook or Twitter, some kind of post goes viral, and they come to us and say, is this true? Is this accurate? Can you tell us why or why not this might not be right? And one of these requests came in recently. I want to start off with this, just to give some framing to what I'll discuss. So you've all heard the expression, a rising tide lifts all ships. But what if all the ships cause the rising tide? So the claim is that sea level is rising because so many ships are being put into the ocean, it's not because of global warming. So this came about, it was on Facebook, shared like 100,000 times, I don't know, whatever it may be. So this reporter from USA Today contacted us and said, this doesn't seem right, but can you actually put some numbers to it? So I had a few reactions when this request came in. So the first was risk versus reward. Should I really engage with this? Do I spend my time doing this and trying to resolve this issue? I can make a simple math mistake, that would be embarrassing. Do I really want to do this? The next question is, how many ships are actually in the ocean? And some of you may have a better answer to that, or some of the people at this meeting, but some simple questions. How many ships are actually in the ocean? This graphic got attached to that Facebook post, so it looks like there's a lot of ships there, but then how big is a ship, right? So if there are all these ships, how big is a ship? How much water could it actually displace? But my core reaction was that it's definitely not true. And the reason we know it's not true is because of the satellite observations we have. So maybe common sense, you could say it's not true, but we can actually put numbers to this. And that's what I want to walk through, exactly how we know immediately that this kind of claim is not true because of the satellite observations that we have. All right. So based on our understanding of the ocean and how climate change is proceeding, we know there's two main reasons that sea level is going up on global scales. So I'm not talking about kind of local, regional scales. We'll get into that more later in my talk, and Mark will talk about that. But on these very broad global scales, there's two reasons, and they're both associated with global warming. So the first is that the ocean is absorbing heat. About 90% of that trapped heat due to the greenhouse gas effect, or greenhouse effect, gets trapped by the ocean, absorbed, and then as water warms, it expands. So there's this thermal expansion. The other is that ice is melting. So the parts of the earth that are covered by ice are warming. That ice that's on land melts, and then it flows into the ocean. So we have these two effects that are happening. So if we take this one step further, we know that on these global scales, if we add up that mass and then that thermal expansion component and then sum those together, you should get total sea level, right? That should add up. We should be able to understand exactly what's contributing and then see that it matches the total. And fortunately, we have observations of each of these three pieces, right? So we have the addition of the mass that comes from the ice. We have the thermal expansion, which comes from in situ observations from something called the Argo profiling floats. And then we have a measure of total sea level from satellite altimetry. So I want to walk through each of these quickly and just explain the observing system we have and what exactly it's measuring. So I'm going to start out with this total sea level, the altimetry piece. All right, so before we had satellites, the main way that we measured sea level was from tide gauges. So over the past couple centuries, we have these tide gauges. This is a map of one of the data sets that's maintained for tide gauges. You can see that these tide gauges are located across the globe. There's a bias certainly towards the northern hemisphere. There's more tide gauges in the northern hemisphere. Most of the gauges are located along coastlines of the larger continents, but you do have some island gauges. But in general, you have a lot of gaps, right? There's a lot of pieces missing, a lot of parts of the ocean that are not being sampled. And if you go back in time, this is the current observation network. If you go back in time, it gets much worse, right? You have fewer gauges, you have stronger biases in terms of where they are geographically. But more recently, we have what we call satellite altimeters. Okay, so these are radar altimeters that are orbiting above the Earth. They're measuring the height of the ocean from space. So from about 1,300 kilometers up, we're able to measure the height of the ocean to about a 1-inch accuracy. Okay, so it's a pretty simple measurement concept. Sending a radar pulse down to the ocean, it bounces off the surface of the ocean, travels back to the satellite. You can measure the time it takes for that pulse to travel, and from that you can infer, after some corrections, infer the height of the ocean. So we get very accurate measurements. This is the Sentinel-6 Michael Freilich satellite. It's sometimes referred to as Snoopy's doghouse. It does look a little bit like a house, I guess, or doghouse. But this is the most recent altimeter that we've launched back in 2020. But here's a little graphic of how it samples. So as it orbits the Earth, it's measuring the point directly beneath it. So it's nadir pointing and sampling a long track. So it has a particular track that it follows over the ocean. Every 10 days, it repeats this track. You can see there it's measuring, this is an El Nino that it's measuring. The satellite itself does not fill in those gaps. That's some gridding that was done after the fact. But you get this complete view of the ocean every 10 days. Okay, so we're able to see the ocean with these satellites. And one other look at this. This gives you an idea of the actual roughness of the ocean, and that you can see the tracks a little bit better. So these are not filled in. So this is starting in 1992. That's the start of our modern altimeter record. You can see how over time you see these different features that are propagating. This is going forward 10 days at a time. But again, we have this complete global view. If you remember back to what I showed with the tide gauges where we had kind of limited sampling, we now see this pretty complete coverage, at least for most of the ocean. All right. And just to note, the record of the altimeters now spans 3 decades. So with the launch of the Sentinel-6 Michael Freilich altimeter, we go back, or we have this record, seamless record, continuous overlapping between all these missions, which allows us to calibrate and validate the different missions. But this record now goes from 1992 on up to present. That Sentinel-6 satellite is still collecting data, so it's continuing to lengthen. So we have this nice long record. And what can we do with it? We can measure global mean sea level. So we average all that data together at each point in time, and we get the trend in global mean sea level. So this is how much sea level is increasing from 1992 to present. The rate is about 3.4 millimeters per year, or 1.4 inches per decade. That may not seem that impressive, but as you start to build up that record over time, you can see that we've added about 10 centimeters of global sea level over the past 30 years. And this rate is accelerating. I'm not showing it here, but every decade, the rate gets about 1 millimeter per year higher than the previous decade. Okay, so we see a very clear view. Some noteworthy things here, there's not a lot of variations there. So whereas some of our other climate records, you see more ups and downs, this is pretty linear with that acceleration I was talking about. So it's a pretty unambiguous increase in global sea levels that we see from these satellites. All right, so stepping through these other two. So we have the total, now we're gonna look at the individual processes, or the individual contributors. So the first one we'll look at is the addition of mass, and this comes from the GRACE follow-on series of satellites. So GRACE and GRACE follow-on, they're 2 separate missions, are actually 2 satellites, one following the other. And the only measurement they're making is the distance between those 2 satellites. So as they orbit the Earth, you can kind of see here, the distance between these satellites changes over time, and they respond to gravity changes on the surface of the Earth, or within the Earth. Okay, so if you fly over, here we can see that example on the right. So as that first satellite goes towards that mountain, it gets pulled towards it. So it feels the gravity of that mass, it gets pulled towards it. The separation between the 2 satellites increases. As it flies past, it gets pulled back. The second satellite gets pulled towards it. So you have this constant interplay between the 2 satellites as they orbit the Earth. So it's actually a really cool type of observation, right? You're not measuring anything directly on the surface of the Earth, but you can start to infer these changes that are occurring. And one of the biggest changes in mass that's occurring on Earth is from the ice sheets. So this is the Greenland ice sheet, the data from the GRACE and GRACE follow-on. So GRACE was launched in 2002, GRACE follow-on in 2020, or 2021. Sorry, that's not right, in 2018, I'm getting my missions mixed up. So there's a small gap between the 2, but you have this nice long record, and you can see exactly where mass is being lost from Greenland. You can show something similar for mountain glaciers across the globe. You can see something similar for the Antarctic ice sheet too. So this can all be done from space using those satellites that I just showed. All right, so if we add up all that contribution, so we can see how much mass is coming off of these sources on land, going into the ocean. The rate of change from this mass-driven component is about 2.1 millimeters per year, so about 2/3 of what we've seen from the altimetry. A slightly different record length, but again, about 2 millimeters per year. So then the last piece of this is not from satellites, but it's the thermal expansion, which comes from these Argo profiling floats. You can already do some simple math in your head. Hopefully this is about 1 millimeter per year of sea level rise, but just to show a little bit of how this works. So these floats go through the ocean, they get moved by the currents, just the general movement of the ocean. And then every 10 days, they go to a depth of about 2,000 meters and then come back to the surface and sample the temperature and salinity within that water column. And then they go to the surface and they report back to the satellite. That data gets collected, and from that temperature and salinity data, we can measure the steric, and in case of the global signal, really the thermal, the temperature-driven change on global scales. And just to give you an idea of the sampling we have from these, this is something I pulled down. This summer, you can pull down the array of floats at any given time every day. But you get a sense of how much coverage we have in the global ocean from these Argo floats. I can then take those, average those together. Again, I already kind of spoiled it, but you get about 1 millimeter per year from there. We can sum these up, see if this works out. And I know there's a lot going on in this figure, but you have the thermal expansion from Argo here. In green is that ocean mass from Grace and Grace Follow-On. In blue is what we have from the altimetry. We can stack those up and see that they generally agree. There's some wiggles that do not, but in general, we have a good understanding of why sea level is changing on these global scales. All right, going back. So let's do some simple math, and please don't check this while I'm doing it, because hopefully there's not a mistake. But so I did some simple Googling. This took about 10 minutes to do. About 6 or 7 minutes of that was just to Google some of these things and try to find as reliable information as possible. But the number of commercial ships in the ocean at some date within the last decade was, I found, to be about 100,000. I'm sure that could be give or take a little bit. Dry weight tonnage of an average ship, about 20,000. Total amount of dry weight tonnage is then 2,000 million. Volume of displaced water you can then convert. We know the surface area of the ocean, and then we get to this final result. The amount of sea level rise contributed by the ships in the ocean is about 5 microns. Okay? So a very small amount. So even though there are 100,000 ships of these bigger ships in the ocean, it's contributing a very small amount. And we know from our observations that the amount of sea level rise that's occurring every day is actually 8 microns. So every day we're adding roughly the equivalent of all the ships in the ocean into the ocean. Okay, so again, that claim from Facebook is not holding up based on these simple checks. We can look at this one other way. So we can look at it in terms of the mass loss the amount of ice coming off of Greenland. So the average displacement of a very large container ship, about 1 million metric tons. The mass loss from Greenland is huge. So the Greenland mass loss that we see is the equivalent of adding 752 very large container ships into the ocean every day. Okay, so that gives you an idea of the scope of the ice that's coming off. This is just Greenland. You have a different contribution from the Antarctic, the mountain glaciers. But again, it's in terms of the sea level rise we're seeing, the factors contributing to it, it's just an incredibly large amount relative to this ship claim that was made. So again, we have the data. We know why it's changing on global scales. And I just want to connect to what Mark is going to talk about with a couple more slides here. So these altimeters I showed do measure regional sea level change as well. So I showed something similar to this. Again, this is just filled in. So not only do we have information on these global scales, we have information on regional and more local scales. And we can take this data and we can compute trends not just over the full globe, but we can compute trends on a regional level, right? So these are the trends in sea level, the rate of rise of sea level from 1993 on up through the present. You can see there's some spatial variability here in California. We have a little bit less sea level rise than what you see in the East Coast. So there's different processes beyond the two that I discussed that drive changes on these more regional scales. But we also know what those are, right? So we know when the water comes off of the ice sheets, it's not going to fill up the ocean like a bathtub. It's going to go follow a particular pattern. We know there's a lot of other signals in the ocean that contribute to this. So just to touch on those quickly, I mentioned the El Nino previously, but there's this large scale signal that we see here that affected here on the West Coast in terms of our sea level that we experience. But we have these large natural variations in the ocean that contribute and can affect the trends that we measure over still these relatively short records. We also have what we call ice sheet fingerprints. So those, and you can probably tell from that computation I did for the ships, that there's so much ice, so much mass coming off of the ice sheets that you're actually affecting the gravitation, rotation, and deformation of the Earth, right? So very near to the ice sheet. So this is for Greenland up here. So right now, there's so much mass there that the water in the ocean actually gets pulled towards that ice, right? It's very massive. There's a gravitational pull strong, it gets pulled towards it. As you start to lose mass, that water gets pulled a little less strongly towards the ice mass. So in the near field, sea level is actually dropping. So if you're very close to Greenland, sea level is actually going down a little bit. The further you are away from where you're losing ice, the more sea level goes up. I know it's a little counterintuitive, but if we're here in California, we're actually more worried about ice mass loss from the Antarctic ice sheet than we are from Greenland, based on these fingerprints. And you can get a sense of that here. So this is just showing where the contributions come from in terms of the ice or the mass contribution for two cities, New York and Sydney. The scale in here is a little bit different at the bottom. But you can see, say, for Sydney, that it's much more affected by Greenland. It's much further away than Greenland, but much more affected by Greenland than what we see from the Antarctic. All right. So to wrap up here, the tendency that we have with the satellite observing network is to start to push to smaller scales and closer to the coast, right? So we know based on the satellites we have now that sea level is changing on these global and regional scales. These are the satellite missions we have. One thing you can note, there's this steepening here. That's overlap of the missions. This is 92 on up through into the future. So we have a lot of these satellites up there that tell us a lot about global and regional scales. But we also want to know what's happening more locally, right? So this is very simple, that because of sea level rise, this moderate safety gap that coastal communities have is much narrower, right? So you have the safety gap where coastal communities are built relative to your typical high tide. You add sea level rise to that, your gap becomes much smaller. So you're really worried about what's happening on these local scales at the coast if we're talking about societal relevance. And again, I've talked mainly about the regional and global. It's this local piece that is most important, which Mark is going to talk about. I do want to note one other satellite mission that is launching in exactly 1 month from today, or a little less than 1 month. This is the Surface Water and Ocean Topography, or SWOT mission. So this is going to get us, again, our push on the satellites is to get closer to the coast and these smaller scale features. SWOT is going to help with that. So our conventional radar altimeters can get us about 50 kilometers to the coast based on the measurement type. SWOT uses this radar interferometry that gets us that much closer to the coast, actually sample on land so it can see lakes, reservoirs, rivers, things like that. But it's going to be able to see these smaller scale features. And I want to end here with this. So this is what the ocean looked like at different periods with the satellite missions. Okay, so this is CSAT, which goes back to the 1970s, GeoSat, which is the 1980s. You'll see the filter be placed over this map for the more conventional altimeters, which I just talked about. So you can see you're starting to get some of that finer scale information. And this last one here will be for SWOT, this most recent satellite. You can see what it looks like. So we're essentially putting glasses on our satellites, right? We're taking this blurry image and we're adding, being able to see this really fine detail, which is really critical, especially as you get closer to the coast. All right, and then one other way to look at this. So this is the sampling we had from the satellites in the past. So this is April 2008. These are the ground tracks with the number of observations we had. April 2008, April 2022, you can see it's a little bit better. If we add SWOT into that, you're going to get that much more coverage. And then if we zoom in here, again, it's a little hard to see, but you're starting to fill in some of these gaps directly at the coast with that SWOT observation. So this is a satellite launching on December 12th. Everybody's really excited about it, and hopefully we can get more information about sea level closer to the coast. All right, so before I hand off to Mark, satellites are providing really good coverage on these regional and global scales, and the push is to get smaller spatial scales closer to the coast. But there's still a lot of important missing information, right? We don't know exactly how some of the shorter timescale processes are contributing at the coast, and that's really what's most important. As we push that baseline up with this kind of global sea level rise signals, it really matters what's happening closer to the coast. And with that, I will hand it off to Mark.
Yeah, thank you so much, Ben. And so happy to see SWOT finally close the launch date. Just for those people who are not familiar with the process, it takes about 20 years to launch a satellite from the first time the engineer walk into a scientist's office and say, if I measure this, what you can do, right? So, so happy. I cannot resist ask you a question. Did you post on Facebook your answer?
Was that the USA Today reporter?
Okay, 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 okay. So second speaker, Mark Marinfield from Scripps. Thank you.
Thank you. Looking at those, that talkie, it's also, all of that was developed after Yi and I came out of graduate school. So in our career, this has been the advancement in this field. And we are young men, so it's not very long. So yeah, I wanted to think about what happens when you take the information you get from these global and regional observing systems, and how do you use it to come right down into the coast, and what additional information do you need to make useful products for understanding when flooding is going to happen and what's going to happen in the future with sea level rise. So there are a lot of products out there now, NOAA, NASA, USGS, where you can get projections on different scales. This is a very nice one that's being put out through the NASA sea level team, and giving you an idea of how many flooding days per year in a place like La Jolla you can expect for different scenarios going forward. And this does a very nice job of not only taking all the sea level variability that Ben introduced, but bringing in the tidal variability, which has an interesting low frequency modulation to it. But the missing piece here is the waves. And for a lot of the coastal zones that we want to protect, the wave component is a big part of this. And so how do you start to think about that wave component? This just illustrates kind of that, a little bit of a budget, but thinking every month of the year for a place like Del Mar, and you want to know what's the highest, 2% highest hourly water levels you get at a place like that. So this is average over about 30 years of data. And so what contributes to those high water levels is the tide, which will vary twice a year as a cycle. The water level that Ben talked about, there's a kind of a seasonality to that, which contributes, and that can get much bigger during an El Nino year. And then the yellow bit is the waves, and the waves can be appreciable, almost as big as the tides during some seasons. So getting the waves right is important for getting these total water levels at the coast. So these are the highest water levels ever recorded. This is just the 2% highest. And just to highlight what happens when we start to increase the sea level, that rising of all ships that Ben was alluding to, just means that in the sea level framework, this red layer is getting bigger and bigger and bigger. And there are more tides and more waves events that reach critical stage. This keeps going up. This is with 2 feet of sea level, which is sort of a low level projection by the end of the century. All year long we'll be at a point where the most severe events that we've seen at Del Mar will be a monthly occurrence. And then on and on from there. So getting this middle layer right is so critical, and that's why the work that Ben described is such an important part of that. But we are still interested in getting these other parts right. And so what about the wave component? So this illustrates for a place just south of here, Imperial Beach, and this is very common for coastal communities in California that exist near river mouths or deltas, right? I mean, this is where the water naturally flows down. So this is a low point on the land. And this community was built up in anticipating that sea level would never really get much above those rocks. And this was just a typical winter storm event. Not even a storm, there's no weather, local weather. These are just waves that are coming from the North Pacific. And the combination of high tide, high regional water level, and high waves has pushed this past the threshold. So a place like Del Mar, or in this case Imperial Beach, they would like advance warning about when these events are coming. They're just keying everything off the tide, and they're not really adding all these components together. And then of course, how does it change with the changing water levels with sea level rise projections? So we're trying to build up a system in California, working with a lot of different partners and agencies that are trying to develop an observing system along the coast that gives us this first look at this kind of data. Surprisingly, a tide gauge is a kind of a common measurement. That's an easy thing to measure from a pier. How high the water gets and how much overrush and where the water got, that's a much more difficult measurement. And there hasn't been really a concerted effort to document this. So we have very little information to validate and improve models of coastal flooding because we just lack the fundamental data on how bad did it get under certain conditions. So the backbone of this is going to be understanding the wave component. And there's a group at Scripps called CDIP. They work closely with NOAA. And they're the stewards of these wave buoys offshore. The wave buoys offshore are being put into a wave model for the whole West Coast. And every 100 meters along the shoreline, there's detailed information about what the waves are, what the period is, direction, average period, wave spectra, and how that's projected going forward for, I think it's like 6 days projections on each site. So hindcast data, forecast data, and this is the information that you'd want to use as an input to something to try and predict why did Imperial Beach flood. That's a tricky, there's a lot of physics in there because this is the surf zone. And so this is the turbulent boundary layer where you have to, given the incident wave height, predict how far the waves are going to get onto the shore. And as they're coming in, they're actively eroding the beach. So this was some measurements we made in Imperial Beach. And during the course of a 4-hour storm, the beach dropped by 1 meter. So you have to constantly, you have to take this into account when you're trying to predict these things. And until recently, there's been very difficult to try and measure these bores as they've been coming into the shore. But now we have LiDAR technology, so laser ranging technology, which is actively giving us the full picture of how the beach is changing, how the waves are changing, how far they penetrate. And so these LiDAR systems are going to be the backbone of the observing system, coastal observing system for California. If you want to do predictions during these active events, you have to understand how the bathymetry is changing, not only at the beach itself, but offshore. There's bars moving around, sands moving around actively. And to get that into your models, you can do through understanding how fast the waves are moving. So the waves in shallow water, they move as fast as the water depth. So if you can track the speed of the waves and do a little bit of math to account for their amplitude, you can back out what the water level is. So this is part of the system, is imaging the waves, understanding how fast they're moving, understanding what the depth is. That gets put into the model for the prediction. At the end of the day, you get these sorts of things. So the blue line here would be like a regular tide chart that you would use. Added onto that is the wave-driven, it's called run-up, or how high the water is getting vertically is associated with the waves themselves. And for different thresholds, you can see that how often it got there through this winter event. And it is how it's manifested on the ground is that there are more and more high tides which are lifted above threshold because of this wave component. At present, for this particular storm, we not only give the expected height, but also the probability, and these are the probabilities of flooding. When you start to add sea level rise to that, this is just 60 centimeters, which was a modest estimate for sort of an end of the century level. You can see how many more of these high tide events become flood events. So this is what's going to happen in the future, is that everybody's going to become a tide expert, and everybody's going to know exactly what the tidal range is, because it's going to be critical. Is it higher than usual high tide? Is it higher than mean high water? And not only is it going to get above flood thresholds, but these periods of flooding, the portion of the tide that is above threshold will become longer and longer. And so this will be what California has to deal with going forward. Having this advanced information has been useful for a city like Imperial Beach that doesn't have a lot of funds to combat this sort of thing, but at least they can get out in front of it with signage and warnings to the public, getting bulldozers in place for moving the sand around. Some shoreline protection can be made. So there is a definite advantage of having this early warning, and then having the early warning system also be the thing that you sort of assess how the long-term projection is going to play out, has sort of a nice public perception piece to it, because people start to understand what the warning is and how that is going to change with sea level rise. That's the ocean-facing shoreline. In the bay, there's also some interesting dynamics, and we've been looking at how the wave component within a bay like in San Diego Bay is going to contribute to, or how you need that to get accurate predictions of flooding around the bay. And just highlighting how kind of right at the threshold we are. So these are the low-lying areas around the bay that are 0, 1 meter, 2 meter, 3 meters above mean sea level. And so these are all within reach of current projections for sort of 2100 to 2150, just showing how much of the surrounding shoreline is at risk here, including, I think, yeah, here we are at Liberty Station up in here. We're going to get up in a little bit of trouble. I think I'll leave that for now. So this the challenge for getting this extreme water level component added on to what Ben was describing is that we need to not only understand the hydrodynamics, but also how the shoreline itself is changing. And so part of the solution here is going to be with satellites and trying to get things like beach width, beach slope from satellite imagery, which would then feed into the predictive skills of these models. This is just getting started out. The accuracies are still pretty low, but as these images get higher and higher resolution, this will become more and more of an important tool. The other part of the problem that we're actively working on is, well, how do adaptation solutions work today? So if you do invest in something like a huge nourishment project, as this is in Imperial Beach, how long is that sand going to be there? How effective it is at beating down this wave-driven flooding? You know, economically, is this feasible, and how long will this be feasible? The other thing we've been looking at is how the water level is seeping into the groundwater and also the sewage systems, and how that's affecting utilities and just the flood infrastructure of of city like Imperial Beach. So that's been an interesting problem, because a lot of the impacts of sea level rise will not just be right at the shoreline, but we'll feel these further inshore as these systems start to become more endangered. I think that's it for me.
Thank you very much.
Yeah. So maybe we can invite Ben here, and then do you have an actual microphone? Okay, so we have limited time to ask each of the two speakers. And then
Yeah, my first question kind of builds on the end, though. I saw where you put the slide up about the groundwater infiltration. How are you measuring that right now? I mean, the impact of seawater coming in on the groundwater.
So we have wells that we've dug into so there are wells around the city. If you dig enough of those sort of going from the ocean inshore, you get a sense of how that water seeps in as a function of different fluctuations in the ocean. So that's been critical for understanding that.
So you're measuring the level in the well, in the groundwater well. Just simply the level tells you the information you need.
It's
okay.
like a tide gauge in the
Right. You don't measure the salinity out of that as well, or?
Yeah, we do, and that's been important too during the rain events.
Right.
Yeah.
Is there any changes in like the permeability of the rock or anything that's?
What we've learned is, so a lot of what we've done in this area has been in Hawaii, which are these volcanic basalt, sort of very, they're like sieves. And here, the water, that's like clay. And so it's not nearly as, the water doesn't interact as much. Yeah.
Okay.
Okay. Any other questions?
So are you aware of any work looking maybe 10, 20, 30 years down the road for bridges, and you know what the impact of sea level rise is going to be on that for existing bridges and potentially for permitting of new bridges?
I don't know of anything specific to bridges. Yeah, I guess I just. Do you have any?
Not really. I mean, I know there's been a lot of concern about the bridges that have been built along wetlands. So a lot of those bridges are particularly vulnerable going forward. But you know, I don't know specifically about bridges, but just basically transportation routeways along the shoreline are susceptible to saltwater flooding, and there's a lot of concern about that.
And Hampton Roads, before I moved to JPL, I lived in Hampton Roads, Virginia, and we have bridge tunnels there, right? So they call them bridges, but they're essentially tunnels. But access to those access points to those bridge tunnels is a big concern with sea level rise, especially because there's not that many routes out of Hampton Roads if there's a hurricane or something like that. So being able to evacuate or clear people off. But yeah, so in general, transportation, I think, and all of that is at risk with sea level rise.
Any other questions?
My wife and I recently, okay, will do.
My wife and I recently bought a condo in Imperial Beach, and we looked at the map, so personally appreciate the work that you've done to decide where we buy that condo. But I was asking a question about, since you've been tracking over time kind of the impact of waves and tidal events and weather and all these things, and the beach nourishment project, which I know has been going on in IB for quite a while. Are you able to use some of that data to say, okay, if you replenish the beach in such a way, it will actually provide additional benefits for coastal resilience?
Yeah, we started to look at that. We have enough data now of the beach change, natural beach change, as well as the fate of some of these replenishment events. And it turns out that with that there are management practices that can keep pace for a while. And I think that the latest thing that we had was that out to sort of mid-century, late to the second half of the century, standard practices should be able to keep the beach width in a reasonable state in many of these areas. But it starts to turn there.
Yeah, I'm wondering about the ocean heat conveyor belts. Are you guys picking up any changes in these giant current conveyor belts?
Yeah, there's a lot of focus on it. And a lot of research going into it. So it's kind of a signal to noise problem with the other types of variability. So there's a lot of what we call interannual decadal scales. So like between 2 and 20-year variability that occurs naturally. So trying to pick out that climate change driven slowdown is a work in progress. We can look back over the full 20th century at some of the tide gauge observations that we have along the east coast of the U.S. and try to infer from there. But yeah, right now it's somewhat inconclusive, and then the models going forward, the recent IPCC 6th assessment report did discuss that the AMOC, that East Coast signal in particular, and there's so much disagreement spread amongst the models about how that'll proceed into the future. But I think that's a very active area of research and need to monitor to understand, because that has a big impact on sea level rise on the East Coast and how quickly it could go up. It also has global impacts, obviously, not just on sea level.
Yeah, this AMOC, Atlantic Meridian overturning, there are some measurements, there are a couple of papers suggesting you can measure the small changes, but there are so many other processes going on, different time scales. So still
convinced that there will be major changes, or does this lack of signal suggest that maybe these conveyor belts are more robust to sea level rise and fresh water?
No, I think the mechanism, the physical explanation, how it'll proceed based on what climate change will do, I think that's solid physics there that you would expect to impact. I think it's some of the model disagreement is on the degree to which it'll impact, say, sea level rise or the ocean, but I don't know if you have thoughts on that too. But
no, I mean, I think that the signal to noise issue is appreciated, so the data hasn't confirmed or dissuaded anybody.
Question first before I go second round. Oh, okay, sorry.
I stole it. I've heard this question a couple of times in other speeches. If you had a magic wand, what's the one piece of tech or the one measurement you could get that would change your lives, or change your research for the better?
yeah, so I didn't talk about this directly, but the range of future projections of sea level is very heavily driven by what's going to happen with the West Antarctic ice sheet. So I don't know if you guys have heard of the Doomsday Glacier, Thwaites, rapid ice sheet loss, whatever the case may be. But right now, the spread that we have on the scenarios we can provide to planners is almost entirely driven by that particular contribution. So if we had dedicated observations of some things that would be like bedrock and some of the different pieces down there in the ice sheets, that could potentially have a dramatic impact on the money being spent for adaptation, our ability to narrow a range. So I don't know, it's an active discussion within NASA as to how do you actually observe these things and get the long-term measurements and monitoring you need. But in terms of a physical process, that would be the one with the most impact.
Monitor ice, melting rate or something.
Or thickness,
yeah.
But yeah, it's also seeing what's below the ice.
That's
and
right,
the relationship between the bedrock of the ice sheet and.
I guess SWOT will do some of those. I think part of the secondary objectives.
Yep. So I mean, SWOT's going to tell us a lot about one thing SWAT will do with these smaller scales, those smaller scale features, those mesoscale eddies and fronts, again, kind of the ocean weather, I guess, the weather that happens in the ocean, plays a big role in the ability for the ocean to uptake heat. So right now, I said 90% of the heat actually gets absorbed by the ocean. It's possible that the ocean could become less efficient at absorbing that heat and then dramatically change how the Earth is responding to climate change. So SWAT's going to play a big role in helping us improve the models for the ocean role and ongoing warming.
Mark, what's your?
Well, I'm the oceanographer here, so I'll go for the ocean. The floats that Ben showed, the Argo floats, are only, for the most part, only getting half the water depth. So there's some interesting phenomena happening at greater depths, and full monitoring of the ocean is just starting to pick up, and so more of those floats. Also, those floats are measuring physical properties, but we're starting to see a new generation that are measuring biogeochemical properties. So we'll start to see changes in the ecosystems as well as just the physical system.
Yeah, that's if you were at the session yesterday, talk about one Argo now not only have a temperature salinity measurement, also have deep Argo go down to 6,000 meters. Biogeochemical Argo also anticipated to increase and then measure the biochemistry, biology, monitor the ecosystem. So,
yeah, just a little spin. That's kind of the question I was going to ask that Graham asked. But I guess I was thinking of all the sensors you use in terms of trying to be a leading indicator of a flood, right? So you have the LiDAR, you have the CDIP buoys, you have the NOAA tide gauges, you have maybe other things that are in the IO system that you didn't mention. If I guess in terms of what the last question was, if you're specifically looking at deploying some kind of new sensor technology to be a better leading indicator for flooding, what would that be? What's the gap right now?
Well, I think it's the documentation of flooding. You know, it's understanding what the extent was, what the duration was, how high did the water get. Those measurements are going to take a slightly different. It's going to be a little bit hard to standardize that measurement because every community is going to require a slightly different retrofit of what would be required to do that. But there's also like a big citizen science component to that, getting more people involved in a post-event documenting what it was, and with cameras and GPS and all that. We'll probably see more of that going forward.
So it's not really more sensors at this point. It's understanding how the impacts of the flood are, so you can use the sensors you have right now more effectively.
Right.
Okay.
Any other questions?
Sort of a follow-up to that. Are the impacts detectable with any satellites? Like, I mean, if you had a high-resolution optical that takes a picture of a flood event, can you derive that kind of analysis from the image, or is that not the kind of data you need?
No, I think that you've probably seen a lot of those slider images, post and pre-storm, seeing the satellite the change in the satellite images. I think that's an important piece, and we're seeing more satellites going up with Planet and other small systems, and resolutions are getting better. We're getting more numbers, so that database will be incredibly useful going forward for sure.
Yeah, within NASA, we have a project called OPERA, which is basically look across the entire network of satellites, the synthetic aperture radar, the optical. SWAT will be a role in this, but to standardize a surface water extent product, which would be able to detect these flooding events and then build that information into models. With any one satellite, it's a little bit of a needle in a haystack. I mean, the sampling for any individual satellite, the repeat orbit could be once every 10 days, once every 20 days. But if you look across the full set we have, and like Mark said, there's a lot of satellites up there, an increasing number, we should be able to capture more of these events.
Ben, I have I cannot forget the Facebook story, so I want to have a question. I think we can launch many more satellites. We can write another couple hundred papers. I don't think the public can recognize that. Still, you have the similar posting, maybe a different taste on Facebook. What do you think we should do, kind of spread out that awareness, kind of, we talk about reaching to the public more, and then try to convey that scientific finding, as far as we can tell, we don't need more satellite to convince ourselves, but how do we convince the public?
Well, I mean, I think a lot of it is done at the university level, engaging students and getting the word out in that way in terms of broader education, in terms of like public outreach and communication. I think that's something we try to do within NASA, but I think scientists are not always effective communicators. So I think it's a work in progress, and we're trying to provide more outlets and avenues. So like I'm the team leader of the NASA Sea Level Change team, and one of our objectives there within the team is to have a public face to put out information that's accessible. So we have the portal at sealevel.nasa.gov, trying to put information out that reaches a broad audience. So I think there is more dedicated effort to educate, but I don't know. It's always going to be an uphill battle, I would say, given the way it's become politicized.
I know we are doing more. When I was a project scientist for the Aquarius mission for salinity, we dedicated a fixed percentage of money doing education, public outreach. I don't think we accomplish what we want to do. So we probably have to change our strategy, do something different.
I should also say that, I mean, with changes in administrations and priorities, that stuff is among the first to get cut, right? The education outreach piece. So it's not always consistent.
I know it's an open question. Yeah. I cannot resist asking. Any other questions? Because those kind of postings are going to happen, next year, next 10 years, right? Yeah. So I think launching one satellite doesn't.
It's kind of a nice story because Ben mentioned the Michael Freilich satellite. Mike Freilich started his career studying wave-driven flooding at Scripps. So that's a whole cycle that kind of,
Yeah, Mike Freilich started PhD at Scripps, and then he was a GPL for a few years, went to Oregon State, being a professor, being the dean, and then eventually went to NASA headquarters, and then very instrumental pushing many of the Earth science missions, including the salinity I work with, SWAT, and watching SWAT being killed, being reborn, and multiple times, and 20 years in the making. It's amazing.
Fortunately, Mike was an oceanographer who got seasick, so he had to make a pivot.
Yeah, just like me. I have one cruise as my last cruise.
I'm at 0 cruises, so it's probably going to stay there.
You need to go to at least once to calibrate what you're measuring from space. That's what I did. All the engineer on the plane, they say, you're the only oceanographer, you are on both. So I said, okay, I did once. Any other questions before we can adjourn to go to the happy hour networking time? Okay, thank you for the speaker.